process. This gives you the coupling strength. Okay, so now let's connect this to something interesting, which I'm showing you here is a phase diagram of the cuprate high TC superconductors. And these are actually layered systems, so they are 2D systems. And you can have of electrons, and you can have holes, for example, doped in the system. And for zero doping, you are basically exactly in this regime of having 1 electron per side, 50% spin up, 50% spin down. And if we look at the phase diagram of the system, you see actually below a certain critical temperature or below a certain temperature level here, you see indeed you get this antiferromagnetic ordering, which is precisely this Heisenberg antiferromagnet we've been talking about. So this really occurs in materials. And as we'll see, it also occurs in these cold gases. So now the interesting thing, what people don't understand today, where there's still huge open questions, is what happens when you start to introduce holes into the system. So you're really trying to understand the competition between hole motion, hole doping in the system, and this antiferromagnetic ordering, and try to understand how this gives rise to all these different very, very weird phases of matter. And this is, I think, one of the biggest problems, outstanding problems in solid state physics, to solve the riddle surrounding this, the puzzle surrounding this phase diagram. So essentially what you are trying to do is you're trying to understand, and this is what we will look about in this lecture today, how does this magnetic ordering, like this antiferromagnetic ordering, compete with the hole motion in the system, where holes want to delocalize to minimize their energy. You remember that a single particle will minimize the kinetic energy if it's in a completely delocalized state, a delocalized wave function in the system. And so we're going to look at this competition between hole delocalization and magnetic ordering in the system today. So now we switch over from the bosons we looked at so far to the fermionic model. And we also have this beautiful tool of the quantum gas microscopes available there, where we can see like individual atoms and individual spins, even, as I'll show you in a second, in a spin resolved way. So we can really say where are all these particles in the system. So here's a first experiment that I want to show you from Markus Greiner's group, realizing precisely such antiferromagnetic systems of fermions in this optical lattice. So remember, you have this optical lattice, square optical lattice. You put 50% spin up, 50% spin down. Fermions in there. Here in this case, these are lithium-6 atoms, 2 hyperfine states from lithium-6. You make the temperature cold enough such that you would be in this antiferromagnetic phase from this phase diagram. And when you take a photo of the system with this fluorescence imaging that I introduced to you yesterday, you see a picture like this one. So you see in a spin unresolved way, you see where all the atoms are in the system, but you cannot say where is a spin up or a spin down in the system. Now, here's a nice trick that you can apply to see where one of the spin components actually is, how the spin's oriented. You can actually remove one of the spin components. Let's say you remove this spin down component by shooting in a laser beam that pushes out those spin down atoms. And then basically you are left with only the spin up atoms. And now you can actually see beautifully from this picture, what we couldn't see from this picture, that if we only look at the spin up atoms, then we actually see, oh, it's really nicely aligned in this checkerboard pattern that we expect for an antiferromagnetic ordering. So actually, you also know where the spin downs are, because each time there's a hole, a missing atom here, you know that must have been a spin down particle if you're coming from a system where every lattice site was originally filled in the physical system, okay? So this works actually very nice, and you can actually look at correlation functions, G2 correlation functions, spin-spin correlation functions, and you see that you need, if you are low enough in temperature, you can have antiferromagnetic ordering, which extends over the entire size of the two-dimensional system. Whereas if you go to higher temperatures, if KBT becomes larger, then this exchange coupling strength, so remember this coupling strength, which is important here, is this exchange coupling. If temperature is larger than J exchange, we cannot expect the magnetic ordering to occur. If temperature is lower than J exchange, then we enter this antiferromagnetic phase here. So if the temperature is low enough, you can indeed see that you get this beautiful antiferromagnetic ordering in the system. Now, one problem with this detection method is that if you have a lot of holes now, if you would dope the system with holes, if you were to introduce mobile holes into the system, and a lot of them, let's say 20, 30, 40, 50% of holes, then of course, when you take such an image where you remove the spin down component, you do not know whether this missing atom here, is that actually a spin down or is it actually a hole, right? Because it could have been a true hole that was in the system as well. So you don't know that. And therefore, this detection method becomes limited. And we need to look at ways how to do this in a better way to image that. And I'll tell you how that works. Okay, let me first start to show you a little bit what you can do with such images. So let's say this is a single picture from our quantum gas microscope for lithium-6 atoms for fermionic particles on the lattice. They are not imaged in a spin resolved way, but they are imaged in a density resolved way. So you see the lattice sites here marked by the squares, and each time there's a bright spot, this is a single atom on that lattice site. And you can really see, we can beautifully see each individual atom on these different lattice sites. You can also see sometimes sites where there is double the fluorescence. So this is actually doubly occupied sites where you have two atoms on that image, on that lattice site. So now you can take such an image like this one and make use of the knowledge of your point spread function, for example, of your imaging system, and use a reconstruction algorithm, a computer algorithm, to take such an image, raw data, and convert it into an occupation of the lattice sites. So this would be then what comes out of this single image, where you can tell now whether the lattice site was occupied or not. If it's occupied, we mark this with a blue circle. If there are two atoms on that lattice site, we mark it with a red circle. And from this picture, we can actually beautifully reconstruct the occupation that we had on the lattice. That's a single picture. So now let's see what we can do if we have several hundreds of those. Well, the first thing you can do is, for example, you can just calculate the average density of your system. So you can take 500 of these images. Each one will be slightly different. Remember, it's a different configuration of the many-body state. And then when you average them, you get, of course, then the average local density in the system, which you can see here. But if you have access to the snapshots, you can do more. You can also look at, for example, fluctuations. What is the fluctuations, the on-site fluctuations compared to the average density, for example? Because in each shot, there might be a slightly varying atom number on that site. You will have a fluctuating atom number on the lattice site, allowing you to calculate the variance on that lattice site. And if you compare that to the mean, you can tell something that's known very well in quantum optics, that is the number that is so-called number squeezing. So how much number squeezing do you have? So remember, for a Poissonian system, the standard deviation goes like the square root of the mean. So the variance goes like the mean. So for a system which would just be, shot noise limited with Poissonian statistics, this number would be 1. And now, of course, we can be in states of matter, in insulating states of matter, like this Mott insulator or a band insulator, where you have exactly a fixed number of particles per lattice site without any fluctuations in the particle number. And then this would give you a actually reduced number, with the number squeezing being smaller than 1, and this telling you quantitatively how much reduced those fluctuations are. And you can actually see here very nicely in this picture that here in this region, in this blue part, you have quite low number fluctuations. But in the surrounding, in the boundary of the system, this is where all the fluctuations of the system are actually stored. And then you can actually also do things which are even cooler. You can calculate, for example, the local entropy. If you remember your statistical physics course, the entropy is just defined by the probability of a certain configuration to occur times the logarithm of that probability. And then we have the different on-site occupations that we can have, 0, 1, or 2 atoms that can occur, for example, in the system. And by measuring this occupation, we have access to the probabilities of those configurations, 0, 1, and 2 on each lattice site. And thereby we can calculate how the entropy is distributed in this many-body system in a lattice site resolved way. So we can even look at these local regions here and say, okay, this is a region with very low entropy, and the ring outside here, the perimeter of this gas, actually carries a lot of entropy, carries most of the entropy. So we can really make also use of this statistics to measure how entropy is distributed in this quantum many-body system. And that's very powerful. And now from all these quantities, you can actually, by assuming that the system is in thermal equilibrium, you can calculate things like the chemical potential, the temperature of the system, the compressibility of the system, which would be just the derivative of the mean density versus chemical potential. So all these thermodynamic quantities you can directly access now from images like the ones I showed you. Okay, so let me tell you a little bit how we realize this spin resolved imaging in our lattice systems, how we can not only say where is a single atom or two atoms, but we can also say where are the individual spins that we have in that system. Okay, so for that we actually prepared in the first experiments a system where we have a 2D system, but where the spacings in the y direction were twice as large as in the x direction. So the spacing in this direction is twice as large as in this direction. You can directly see that. And these intermediate lattice sites were not occupied, or they were held at a higher potential. And now we can make use of this system to basically now have a spin resolved detection in the following way. We can do the following trick. Let's imagine you have a one-dimensional chain like this one. Let's take 1D chain here, and you want to see now where are the spin ups and downs in the system. So in order to do that, what you do, you take this 1D chain that we have here, and you make each lattice site here, you split into two lattice sites. This is done by introducing a lattice potential which has half the wavelength, half the period of the original lattice. So you can basically split each lattice site into two lattice sites. So it's like out of a single well, you make a double well. Okay, out of a single lattice site, you make a double well lattice site. And now if you do this splitting process, well, let me actually ask you, if you would just, let's say you take a single atom and you just start with a single harmonic oscillator and you turn that into a double well, where does that single atom end up? See what I mean? You start with a single well, the atom is in the ground state of your harmonic oscillator, you split this now into a double well potential, and you do this adiabatically, and the question is, does the atom end up on the left-hand side, on the right-hand side, or where does it actually end up?
Superposition.
What would you say? Yes, superposition of what? Can we say what the state would look like? Both wells superimposed, that's correct. But how? Yes, any of the two wells, that's correct. But can we say something about which superposition state? Remember, if we have the left wave function and the right wave function of the double well, then we can form any linear combination of the two. But let's say we just want the one with plus and minus sign. Which one is it going to be, the plus one or the minus one?
So according to the adiabatic theorem, it should be the new ground state.
Sorry? Can you repeat?
According to the adiabatic theorem, it should be the new ground state.
Yes, and what is the new ground state? That's correct. And what is the ground state of the double well?
I think it should be +1.
The symmetric?
Yes.
Symmetric or anti-symmetric superposition? So in the double well, you have the two states, which can be psi left plus psi right, or psi left minus psi right. Which one is it going to be?
Should be the symmetric.
Yes, it's the symmetric one, right? Correct. It's the symmetric superposition that you get. You would be delocalized. So when would you end up actually in the anti-symmetric? Is there a way you could see how you end up in the anti-symmetric superposition? What would you have to do if you have a single atom on this single side? How do you end up in the anti-symmetric superposition?
If the splitting is fast enough, then
we want to do things adiabatic. So we want to put quantum state to the other one. So from which quantum state do I have to start in the single well to end up in the anti-symmetric state in the double well? What would you say? So basically, we're trying to find out how are the states in the double well connected to the states in the single well. Anybody have an idea? If you look at the wave function, we have, let's say we want the state I'm asking about, the anti-symmetric one is psi left minus psi right. which wave function is that connected to in my single well? First excited state, excellent, very good. That's the first excited state, because remember, that's also, it needs to be an antisymmetric state, right? It cannot be a symmetric state from parity arguments. And the lowest energy state that we have that is antisymmetric is the first excited state in the harmonic oscillator. If you remember your Amide polynomials, the ground state is the Gaussian, and the first excited state is this wave function, which is antisymmetric. So that's precisely the one that you merge to if you would be in the in that excited state. Okay, but now we want to do even a little bit differently. Now I want to do the same splitting. We start in the ground state of the single well, and now I want to do the splitting, but I want to add a gradient. I want to split now from a single well into a tilted double well. So imagine you have the double well, and now the double well does not have equal energies on left and right side, but it's tilted like this. So where do you end up if you split into a tilted well? You start out with a single well, and now you go into a tilted double well with large tilt. Where do you end up with your atom? Does it come to the left side, to the right side, or does it go to the superposition, symmetric superposition state again? What would you say? So you start in the ground state here, and you go to this very tilted configuration where one well is much deeper than the other well, much lower in energy. Yes, so indeed, if the tilt is large and you do it slowly, you end up, of course, in the deeper well. Because if this well is much deeper than this one, then the ground state of this tilted double well will just, of course, be the lower energy state of the tilted double well. And then if you just do everything very slowly, again, you stay in the ground state, adiabatic theorem, then you just end up in the lower well, in the right well. Perfect, very good, you understood that. So now we can do this tilting. What is a tilted double well? Well, tilting a double well, it just means you have to apply a potential gradient. If you apply on top of the symmetric double well, you apply a gradient, you tilt the double well, right? You end up with this tilted double well. And now we can apply this gradient by applying a magnetic field gradient to the atoms. And because the atoms have different magnetic moments, this potential gradient will point in one direction for the spin down particles and in the other direction for the spin up particles. So for the spin down particles, let's say the right well will be the lower well, and for the spin up particles, the left well will be the lower well. And if you then do the adiabatic splitting, as I show you here, then the following is going to happen, that the spin down particles are going to go into the lower lattice side of the double well, and the spin up particles are going to go into the upper lattice side of the double well of the corresponding tilted double well, right? And this is how we can separate spin ups from spin downs into spatially two disconnected 1D chains. And now if we take a photo of these two chains, of these two independent chains, then I can get the occupation of this upper chain and the occupation of this lower chain. But because of the splitting process, I actually absolutely know that the upper chain was only occupied by spin up particles and the lower chain was only occupied by spin down particles, right? And then I know the original occupation of my 1D chain because I just have to sum these occupations up, and then I know what I had originally. So let me show you how this works. So this is the 1D chain, the original system, for example. And then we do this for a different 1D system because, you know, once you remember, once it's photographed, it's destroyed. We cannot use it again. So we have to recreate psi again. So once we create this state again or another one, we can do the splitting process. And now we split this one line into two lines. And I know that the lower lines, those are the spin down atoms, and the upper line are the spin up atoms. And now I can directly read off from the picture what the original occupation of the original 1D physical system was. So for example, let's go through this slowly. This is the first site. It has been split into double wells, so it has two sites now for detection only. And originally, this was one site. And now you see there's no atom in the upper chain, no atom in the lower well. So this was no atom on the original physical lattice site. So no atom on the first site, mark it. No atom on the second site, mark it. Then we have a spin down particle, followed by a spin up particle, followed by a spin down particle, followed by a spin up particle, 2 spin down particles, 1 spin up particle here, and here on the last side we actually had a double occupancy. We had a spin up and a spin down particle on the same lattice side. So this is how you can see how you can actually reconstruct by doing this, actually what we call a controlled Stern-Gerlach experiment. You remember the very famous Stern-Gerlach experiment on atomic beams. What you're doing here is exactly a Stern-Gerlach separation experiment in a very, very controlled way in this double well, where you basically split the single well into a double well, 1 mode into 2 modes under the action of a magnetic gradient field, which splits the spins into different positions in space, and that's very powerful now. So now you can take these spin resolved images. Okay, any questions to this detection method that I show you here? So you have
can I add something?
Yes, please.
Okay, in the spin unresolved picture, it seems that in the second entry of the first row you have something, but then in the spin resolved, then when you do the double well, there's nothing. So why does this happen?
Yeah, because this image, what you see here, is not this chain. Remember, when we take the photo, the system is destroyed and we cannot split it anymore. So what was done, a new chain was prepared. Okay, a new chain where this chain is not this corresponding physical chain here. Okay, so just think of this. The physical chain underlying this split chain for detection that you see here is just the one that you see here. Okay, so this is just an example of showing you a image where we were not able to do the spin resolution, or we didn't do the splitting, but it's a different realization. Remember, each time we make a photo, it's a random picture that we get. Okay, because of the random configurations that underlie the many-body state. Was that clear?
Yes, thank you.
All right. So here I show you this charge. This is now powerful. We can see this 2D picture now. We have a charge unresolved system or density unresolved system. And now if we do the splitting, we suddenly get pictures like this one, where we can suddenly see where each of the spins, spin ups and downs is actually present in the system. Okay, I want to show you a new method how we do that. Since you understood the 1D chain method, I want to show you a bit superior method, which we used recently to do similar kind of things in 2-dimensional systems. The disadvantage of the method I show you here is that we always need this larger spacing in the y direction to squeeze in the atoms here for detection in this direction. And we don't like that. We want the separation of the atoms to be as close as possible to each other. Do you have an idea why we want that in the experiment? Why do we want the atoms, the lattice spacings, to be as small as possible? Is there anybody who knows why we would want the lattice scales to be as short as possible? Any idea? What does that mean for the tunneling coupling, for the tunneling energy, this T parameter or J parameter that I showed you? How does that change if I make the lattice shorter spaced? How does the tunneling matrix or the tunneling coupling change when you make the spacing between the 2 wells shorter? Does it become larger, smaller, stay the same?
Larger tunneling.
Yeah, so it will become larger, the tunnel coupling will become larger, and that's of course what we want. We want the energy scales to be as large as possible, so we don't have to cool the system so much to see this interesting many-body phenomena. Because remember, the temperature has to be lower than this hopping or exchange energy scales to see that. So we want to drive those energy scales as high as possible. And of course, if now we have to introduce twice the spacing in this direction here in order to squeeze a line in between, then we actually don't want to do that, because that will reduce the energy scale in this direction a lot, because the wells are now separated quite a lot from each other. So I see there are a lot of questions now. Should we go through them? And, yes.
There is a question from Sourav. Sourav, why don't you ask directly?
Hi. So from shot to shot, how stable are these lattice? I mean, the grids that you have drawn, are they stable from shot to shot?
Yes, they are quite stable from shot to shot. on a hour scale, hour time scale, they can drift a little bit. Why do they drift? Remember how we make them. We make them by interfering two laser beams, right?
Yes.
So anything that changes in the beam path, for example, a mirror that moves a bit mechanically, or your thermal expansion, the temperature changes a bit in the lab, so things change, then of course that will change the relative phase of those two beams interfering, and that will change the position of the lattice. So we have a very good temperature stabilization in the lab to try to minimize such fluctuations. So that will lead to a very slow drift of the underlying lattice. It will stay a square lattice, it will just move in position. The good thing is that, you know, when we see single atoms like this one, we can always, from a single shot, we can tell where the lattice was, what the phase of the lattice was. So we can use a few of these individual atoms that we detect to know where the phase is and predict where the phase is going to be in the next shot, for example, for the experiment. Because we know the drift is slow, we know that from one shot to the next, it will be the same stable lattice, but maybe over 6 hours, it will move. So, but we can keep track, by knowing the position of the atoms, we can keep track of this phase drift of the lattice, and we can correct for it. For example, this is very important. You raise an important point. When you want to address a certain lattice site with a laser beam, want to focus a laser beam onto a certain site, you need to know where to shoot the laser beam, right? You need to know where the lattice site is. So this is a very important question you ask. Very good.
Okay, thank you very much.
Any more questions?
There is one from Mrinal Kanti Giri. At empty site, there is also some finite probability in spin resolved pictures. Why this happen?
Yes, so there's a little bit tricky thing I didn't really explain exactly. So you're probably meaning, well, first of all, there's a little bit, of course, the image of a single atom, you know, is well, let me ask like this. What determines the size of this blob, of this individual blob that represents a single atom, the fluorescent spot of a single atom? What determines the size of this blob actually? What would you say? I mean, an atom, you know, what's the size of an atom? That's 10 to minus 10 meters, right? An angstrom. So we're not seeing this blob is much bigger than an angstrom. We are talking here about separations between lattice sites of micrometer scale. So what determines the size of this blob that I'm seeing there? What would you say? No, it's not the interaction cross-section. It would even happen for non-interacting particles. So this atom here is totally isolated. It's not interacting with anything, right? It's totally
diffraction limit.
I think de Broglie wavelength.
Diffraction limit.
Of what? Yes, diffraction limit, correct. Of what?
Of matter waves.
No, not of the matter wave.
Light, of the light.
Yes. It's
detection.
Yes, it's just, of course, remember, it's our objective. We have our detection objective, and that has a finite resolution. So it has a certain aperture, it has a diffraction, it has an Airy function, right? As the point spread function. This is what it is basically. So this optical lens produces a delta function spike in the image plane, gives us, in the object plane is transferred to a point spread function to a broadened blob in the image plane because of this finite resolution of the system. So what we see here is just the resolution of the objective. So of course, in the resolution of the objective, it becomes on the order of the lattice spacing, a little bit of overlap. We have a little bit of spreading into the different sides. There's another thing that happens here that I'm sweeping a little bit under rug, that we actually have an even finer lattice underlying this physical lattice to do the detection, but I don't want to go into this. So there's a reason why these positions are slightly not centered, that the center of mass of these point spread functions is not always centered on the physical lattice sites, and there's a reason for that, but I don't want to tell you right now. It complicates things too unnecessarily, okay? All right, good. So let me tell you another way how we do this, which is pretty cool. We do a better way to keep the lattice separations short in this 2D regime. So this is, imagine you have this configuration of spin ups and downs, double-ons, hole in the system, and we want to detect it. So an even better way of doing that is the following trick. We separate the planes, again, the spin ups and downs, but we do it with the whole plane. So I take the whole plane and take the spin up atoms and move them into the upper plane, and the spin down atoms and move them into the lower plane of the system. And then if I'm able to do that, and I'll show you in a second how we do that, how that works. If we're able to do that, then you can just take your lens, focus onto the lower plane, take a fluorescence image of the lower plane, then you move the lens, have the upper plane in focus and take a photo of the upper plane of the same physical system, and then you have two images of the spin ups and the spin downs, and you reconstruct the original image in your system again. Okay, so how does that work? So it is a bit tricky, but it underlies some interesting physics, so I want to tell you how this actually works. So imagine this is our single lattice site that we have, and this axis is the z-axis in which we want to split. So imagine you have spin ups and downs on this single lattice site and you want to separate them. Well, to separate them, we just learned in the 1D system, I can apply a magnetic gradient field, convert this into a double well, the spin down will go to the left side, the spin up will go to the right side. This is the same trick we used in the lines, but now we're just doing it in the vertical direction. Okay. Now the separation here is just going to be the separation between these double wells. And unfortunately, this separation is not large enough to already image the two planes independently because they're just too close to each other. Okay. So because why would that matter? Because remember, our optical imaging system has a lateral resolution of the order of lambda. But when you have a lateral resolution on the order of lambda, this also means you have a depth of focus, which is also on the order of lambda. So this thing, this upper thing will not be out of focus, this second plane, and you will see them both on top of each other, and you don't want that. So we have to separate them more. How can we separate them more? And you can separate them more by a process so-called topological charge pumping, where you time modulate the potentials. So we time modulate these optical potentials in the following way. And in that way, you can actually increase, in a controlled way, increase the separation between the layers. So each time what's happening, if you're familiar to this, let me explain it in a simple way. What's happening here is basically a Landau-Zener sweep in a double well. So imagine you have your double well here. Wait, let me stop this animation here. Let's say you are here in this configuration, okay? And you want to transfer the atoms to this well. So, and you have a coupling between the two wells, which is given by the tunnel coupling. But now they are off resonant because there's a detuning delta between those two modes, like in a two-level system, okay? So now if you sweep with your laser in a two-level system, you sweep through resonance, you can adiabatically transfer all the population from one state to the next. So now we do the same thing. We just decrease the detuning. You see here how the detuning changes, how population is now transferred from one well to the next, okay? And then you do the same thing again, transfer again, adiabatic sweep again, and like that, you can actually increase the separation between the two planes in a very, very controlled way. And this works really great. So here are some images looking on the side of the atomic plane. So we're taking a side view onto the plane. You're seeing one plane. And then we do this pumping process, and you see how these two spin states are now more and more split in space. And now we can take two images nicely because now the separation is about 30 micrometer. And when we take a photo of the lower plane, the upper plane is totally out of focus and we won't see it and it will not disturb the image of one of the planes. So this is how this looks. You start with one monolayer, the physical system. You first do the spin splitting, and then you do the charge pumping to increase the separation, and then you take a photo. This is the photo of the spin up atoms. This is the photo of the spin down atoms. And then you can actually take those two photos, just put them together, and you get the original occupation of the 2D system. Okay, so now I know really in a fully spin and density resolved way, I can see where all the spin ups and downs were, where there were doubly occupied sites, where there were holes. So I get a full spin and density resolved image of my system. Okay, so this is now extremely powerful because we want to know how, for example, holes influence the magnetic ordering in the system. Remember, that was our original question, but now such images, as I'll show you now next, will allow us to do that. Okay, I see there's a question here. Will there not be nearest neighbor hopping when this is done? Yes, so this is what we have to avoid. We absolutely have to avoid that during detection, an atom that was originally on one side moves to the neighboring side. So what we do in the XY plane to avoid that is only for detection, we make the XY lattices very deep so the atoms cannot move anymore in the XY plane. Remember, the tunnel coupling laterally changes exponentially with depth. So the deeper you make the lattice, exponentially lower your tunnel coupling becomes, and eventually it becomes 0. So when you make the lattices very deep, you suppress hopping in the XY plane, which we do for detection actually. So this is a good question. We really need to ensure that during detection, the atoms do not move, that the physical, that the image I show you here is really a faithful image of what has been going on in this monolayer of the system. Okay, and this is what, of course, we did do a lot of checks to ensure that that's indeed the case. All right, any more questions to this detection method of seeing this fully spin and density resolved images in our lattices for our Fermi gases?
So both images were taken in the single shot. How? I mean, two laser shots were given one after the other, or how are the images?
There's one physical system. Okay, we do the splitting. So now we have two planes, one occupied by the spin ups and one occupied by the spin downs. And then we can first take a photo of the lower plane, and the upper plane is still there. It's filled with atoms, the ones that we had there originally, right? And then we just move the lens and take a photo of the upper plane.
The first flash of light does not change the state of the, let's say you're taking the image for the top layer.
Yeah.
To shine some light, does it not change anything?
Yes, we have to ensure that it does not change the occupation of the upper layer. Indeed. Okay. Yes. That's absolutely crucial, that you, when you make these images, you do not disturb the other plane, basically. Absolutely. But that can actually be ensured. Okay, and just a check showing you again these two-dimensional antiferromagnetic correlations. When we saw that, we were quite happy because it showed us we indeed have quite nice antiferromagnetic correlations, and we see them in the detection, so we know the detection works well. Okay, I see some questions more. What are the numbers under splitting and charge pumping? Yes, so this was just the separations that we start out with. So originally, the original separation here in this direction was only 1 or 2 micrometer. But then when we do the charge pumping, we can separate the planes over large distances, over 27 micrometers. And that's much larger than the wavelength of light that we use to image here. So that's much larger than the depth of focus of the imaging system. So again, the important point is if I now focus the lens on this plane, the other one will be completely out of focus. And this is what you see. Look at this picture. This is the upper plane in focus. The blue atoms are still there. They're also fluorescing, but they're totally out of focus. You cannot even see them on this picture because they're out of focus. So we have to move the lens to be in focus with the lower plane, and then we see the lower atoms and the upper plane out of focus. But in order for to have a good separation between in focus and out of focus, you have to separate the planes over a distance which is much larger than the depth of focus of your imaging system. Yes, and these separations were only in the vertical plane. That's correct. Okay.
I have a question.
Yes.
So this is spin sensitive measurement.
Yes.
So do you use polarized light?
No, no polarized light. The whole, it's all unpolarized light. You see the whole spin sensitivity only comes in this step here, in this second step. Let me show you again. In this step, this is where the spin sensitive part happens. In the first step, where we split a single well into a double well. And why is it spin sensitive? Because we're applying a magnetic gradient during the splitting. And a magnetic gradient, remember, the two atoms have, in the two spin states, have opposite magnetic moments. So the forces they will experience are opposite. So one is pulled to the right well, and the other spin is pulled to the left well. That's where the spin sensitivity comes from. Okay, it's only from this magnetic gradient field that we apply. All right, any more questions, comments? Discuss? Okay, all right, so now you know our detection process. So now we're ready to do some physics with this. And this is the first thing I want to show you that we actually did last year. It's actually an interesting experiment where you try to do the impossible for a free space elementary particle. So imagine you have an electron here, and the electron, you know, has two quantum numbers, the charge quantum number, and it carries a spin quantum number. Now in free space, you cannot separate the electron into two objects which only carry the charge or the spin. But I'll show you actually in a solid state system, you can do that. You can inject an electron into the solid state system or remove an electron from the solid state system and create two so-called quasi-particles in the system, which carry independently the charge and spin quantum numbers in the system, and which actually then can completely separate from each other in the system. Okay, so let me show you how that works. All right, so let's take this 1D chain, Heisenberg antiferromagnet. In the system, you have this up, down, up, down, up, down, up, down ordering. And let's do the following dynamical experiment. Let's take our laser beam and focus it, shoot it onto one side to push out one of the atoms here. It's like removing suddenly an electron from the system. So then, after you remove that atom from that side, you will have a hole here, and the system will dynamically evolve because now you're not in the ground state anymore of the system. So now this hole will start to move, and you see what this hole is doing. It will just, for example, tunnel. For example, how does the hole move? Well, the hole moves by this particle. If this particle tunnels, this is an empty site, right? So this particle can now tunnel into this empty site. Remember, we are still in the regime of strong repulsive interaction, so we cannot put atoms on top of each other. But if there's an empty site, there's nothing preventing this atom moving over here. If this atom moved over here, it's like the hole has moved to the right. So now this atom can move over here, and the hole has moved another space. And then basically this atom can move over here, this atom can move over here, this atom can move over here. So you see that actually this hole now starts to move. It delocalizes in our system. But if you look a little bit careful, there's another object that has been created. There's another object that has been created that are these two parallel spins in this process, which I just sketched. There's another thing we created. And this other thing we created is actually the other quasi-particle. This is one of the quasi-particles. We call it a charge-on or a hole-on here. This is what this quasi-particle is called. It carries actually the quantum number of charge in a charge system of +E. And this here, this object on the other side that we've created is called a spin-on. This is the other elementary particle which actually carries the spin quantum number. So remember, we had originally a electron here in the chain, or an atom, which carried spin and charge. We removed that particle, and suddenly we get the hole, which moves in one direction. And the other direction, we get another quasi-particle, this spin-on, which carries the spin quantum number. And if you draw this cartoon a bit further, you will see that this spin-on and hole-on, they can move, they can separate over arbitrary distances from each other. So they become spin-on, the spin quantum number and the charge quantum number in this 1D setting have become deconfined. They can separate from each other, and you've done basically what seemed impossible for an electron in free space, where you cannot separate, the spin from the charge of the electron. In a condensed matter system, you can actually do that, and this is how this process actually works. Now, there's one characteristic feature of this spin-on and hole-on is that both of them actually propagate with quite different velocities. So let's estimate this. What would you say is the velocity with which this hole moves? So how fast does this hole move, or what would be, on what parameter in our underlying model, in the Hubbard model, will the velocity of this hole depend? What would you say? What determines the velocity of how fast this hole moves? And the tunneling strength, very good. Indeed, the tunneling strength will determine that. Remember, the time scale for hopping from one side to the next is given by h bar over t. So basically, the larger my tunnel coupling is, the faster the hole will move, or these particles will tunnel in here, or the hole will move. So indeed, so the hole will move at a velocity which is given by the tunneling strength. Now, what about this spin-on object here? What do you think could be the time scale at which this spin object moves? So what will happen? How could this spin object move? The spin-on could move, for example, by these two spins exchanging position. So this green spin moves over here, the red spin moves over here. then you have the two green spins here, and it looks like the spin-on has moved from here to here. What?
The interaction parameter.
Sorry?
The interaction parameter J.
The interaction, the exchange energy scale J exchange, this 4t squared over u strength, exactly. That's what determines the velocity of this particle. And both of them are, so one goes with t, the other one goes with t squared over u, so they should be related to each other by t over u, which is just a factor between them. So one is fast, the charge velocity, and one is slower by a factor t over u, which is the spin-on velocity here. And we can measure that. How do we measure that? So let me show you the experimental data. So this is the lattice position in our optical lattice of the 1D system. This is evolution time on the vertical axis. And now in terms of tunneling times. And now I basically at time t equals 0, I shoot out one atom on this side. So you see the hole density is 1 on this side. So you start with the localized hole. And now you see actually how the hole starts to spread. And you start to actually see what we already recovered yesterday in the lecture. You just see what the probability distribution of the hole is after some evolution time. That's just a quantum walk of a single particle. Because the hole just behaves like a single particle that we would put in the lattice. After some evolution time, we get the probability distribution of a quantum walk. And this is precisely what you see here. You can determine the velocity of the walker by just looking at the cone here, how fast the width of this distribution changes over time. Now for the spin-on, we can actually also measure its spin velocity. That for the spin-on, we can also look at create this up arrangement right next to each other at time t equals 0. And we can look how the next neighbor spin correlations here evolve in time. And we can also see how they spread in time. There's a little bit less structure in there because the temperature is a bit higher in the spin sector. So we don't see the coherent feature, but we still see this kind of cone spreading out. And from that, we can determine the propagation velocity. Yes, so there's a good question. Why is the hole density 0.7? That's just an experimental imperfection. So basically, we were not able to, with 100% probability, shoot out a hole in every run of the experiment. Okay, but we're pretty, and you also see its experiment also a bit imperfect because ideally, we would have only liked to shoot out a hole here at the central site, but you see it always also there's a little bit of probability also of having created the hole on adjacent sites. So these are some experimental imperfections that we have in the experiment. All right, so now we look at the data. We take the width of those two distributions, plot them as a function of time, and you see actually for the holes, they have this very fast spreading. For the spin-on, for the spins, you see this very much slower spreading. And you can directly measure these two spreading velocities in the system. And indeed, if you calculate the ratio of both of them, you indeed find that the ratio is precisely this T over U ratio that we would have expected from the theory of the super exchange interactions. Okay, I want to show you now a more interesting correlation function, and which brings us to these higher order correlators, which are interesting to characterize processes like this spin charge fractionalization of the electron in a much better way. And the correlator I'm looking out for now, the correlation function, is the following one, where I am asking the following question: how does the spin environment around holes look like? So how is the spin on site I-1, this side here, correlated with the spin on site I+1 over here, okay, conditioned on having a hole in between? So this is what this correlator measures, what it tells us on this correlation function. So you're evaluating how does the spin environment look like surrounding a hole. And then, of course, you can calculate the expectation value of that. Now, let's take this chain here and look what this looks like at time t equals 0. At time t equals 0, when I kick out the particle here, I will have a hole here, and the spin environment around the hole will be ferromagnetically aligned. So the spin here and the spin here will be aligned. So this correlation function at time t equals 0 will be larger than 0, will be positive, because these two spins adjacent to a hole at time t equals 0, when I kicked out the particle, will be positive. Now, when time goes on and the system evolves, remember the hole is moved in one direction and the spin-on is moved in another direction. And then actually, if you look at the correlation function of this spin-hole spin correlator, again, which measures the spin correlations around holes, you actually find that in this case, now at later times, the hole has antiferromagnetic correlations surrounding it because the spinon actually has moved in the other direction. So the spinon that was originally attached to the hole at time t equals 0, when we removed that particle, has moved away. So that spin 1/2 degree of freedom has moved away, and you're left here only with these antiferromagnetic correlations around the hole. And this is a direct measurement of the fractionalization of the spin and charge of the particle that we removed from the system, actually. So here's how this looks like in the data. So we're plotting this spin-hole spin correlator, just looking at these thousands of snapshots from our system after kicking out a single atom at time t equals 0. And we see it starts out positive. And then as time goes on, you see how this goes negative and then settles onto the background value of this antiferromagnetic correlation around the hole. And the other spinon has moved away from this hole. So you can directly see this fractionalization process in this 3-point correlation function. Okay, I want to actually show you how this dynamical feature, what we call spin charge separation, you understand, I think now why it's called spin charge separation, because we removed this particle and the spin degree of freedom separated from the charge, or in our case, density degree of freedom. So this is why this process is actually called spin charge separation in condensed matter physics. So what I want to show you now is actually a very intriguing connection to the ground state physics of the system that directly reflects this dynamical behavior that we got when we kicked out one of the particles. So I want to look at the 1D case, and I want to basically now ask, what is the ground state of a 1D Heisenberg chain, antiferromagnetic Heisenberg chain, when I put holes into this chain? Okay, how does the ground state of the 1D antiferromagnetic system looks like? And there, to answer that question, you again have to think about the two things that minimize energy. So for holes, remember, they minimize kinetic energy by delocalizing. Spins, on the other hand, in this antiferromagnetic Heisenberg model, minimize magnetic energy by aligning antiferromagnetically. Okay, so if I look at the ground state of a, let's say, 1D chain with a hole and ask what is the lowest energy many-body state that I can have, then it would be of the following structure, where you have antiferromagnetic alignment of the spins and the hole being in a superposition, being everywhere on the chain. It's completely delocalized, the hole. This is where you minimize the kinetic energy, just like plane waves in free space for a particle minimize kinetic energy. These extended waves in the lattice, these Bloch waves, minimize the kinetic energy of our hole also. So it's in the superposition of being everywhere. But note that in the ground state of this system, it's actually favorable to have antiferromagnetic alignment around holes. Why is that? Well, imagine that this particle moves in here, over here, then of course it would be much more favorable for this particle to be oppositely aligned to this one to minimize magnetic energy cost. Okay, so this is the ground state of the system. This would be the first excited state, for example, but this is how the ground state of that system actually looks like. So to picture that a little bit better, to understand a little bit better, this is actually quite a remarkable thing, because what this single hole does, is to affect not only the vicinity of the hole, but it really affects the entire system. So let me show you what I mean by that. Let's imagine we start out over here to the left of the hole with an alignment down, up, down, up, down, up, down, up. Okay, so this type of alignment, and then comes a hole. Okay, if the hole would not be there, I would continue here with down, up, down, up, down, up. But now I have a hole here, and we know in the ground state of the system, the hole wants these two adjacent spins to antiferromagnetically align. So I go on here, actually not with up, down, up, down, up, down, but I continue with down, up, down, up, down, up. And if I denote these two configurations of the antiferromagnet that I can have by their parity of plus and minus one parity, then you actually see that a single hole is like a domain wall, introduces like a domain wall for the parity of the antiferromagnet to the left or to the right hand side of this domain wall. Okay, so you get a parity flip in the antiferromagnetic ordering. And what's also interesting about this hole is that this individual hole actually is a so-called topological excitation. What do we mean by topological excitation? Typically, if we make a hole in a 3D system or an impurity in a 3D system, it only very locally affects the environment of the system. In 1D here, this is very strange because this one hole here not only affects what happens in the immediate vicinity of this, but affects the spin thousands of lattice sites away of it by imposing this ordering of the antiferromagnetic system, right? So this single hole has a very, very non-local effect on the entire many-body system, and that's why we call it a non-local topological excitation, because it has this effect on the entire state of the many-body system. All right, let's okay, so there's a question actually, to which direction will the hole move? Yes, that's, I just moved, you're completely right. Well, you can answer, try to answer yourself. Let's say we would kick out, you're in the dynamical experiment again. So imagine we remove a particle and we have a hole here, to which direction will it move to? Very good question. So what would you say? Which direction will the hole move to? Think of it as a particle. Think of it as a localized particle in an empty lattice. Which direction is it going to move to? What would you say? A few more guesses. There's somebody already wrote in the chat. Let's see more ideas. Lower energy, yes, it will lower its energy by delocalizing, but in which direction? It's not going to, diffusion is not right. It will not diffuse. It's a ballistic propagation. Actually, you can, that's a good question actually, with the diffusion. Look at how the hole spreads, the width of the probability distribution of the hole spreads linearly in time. So it's not diffusion. What would it have to be for diffusion? If it would be diffusion, what would be the width of the probability distribution as a function of time? If it would be diffusion. So how is the width of the probability distribution of the particle connected to time if for a diffusive process or a ballistic process? What are the differences? Yeah, just go ahead. You can just unmute yourself, chat, whatever channel you want to use, you can use. For ballistic, we saw here it's linear in time. But what is it for diffusion? Ah, it's very good. Square root of t. Perfect. Thank you, Suman. So square root of time for diffusion process, random walk process, but for ballistic process, this is linear in time. So it's not diffusion. It's just ballistic propagation. And ballistic propagation is just like a single particle on a lattice. And remember, that's just our quantum walk. And if you ask me, does it go to the left or to the right? Well, it goes in both directions, right? The wave function spreads out symmetrically to the left and to the right. And only when we make a measurement, we will find the particle somewhere in this region where the probability distribution is non-zero. Right? So we cannot even say whether the particle moves left or right. It actually moves in a superposition left and right. And when I draw these sketches like the one here, you should always keep in mind, when I draw a sketch like this is just one possibility of how the atom could have moved. Just one configuration, one cartoon configuration. It could have moved in the other direction. Actually, in this process from here, it can not only propagate further, it can of course also propagate back, right? So this particle can move in here, and then the hole would have moved back. So we're back to this quantum walk, where the particle in each point in time, it can move to the left or to the right. And the result of this quantum walk is this quantum walk probability distribution. And this is what I showed you here, what you actually also recover for the hole. This is why the whole probability distribution after some evolution time looks exactly like the probability distribution of a single particle on an empty lattice. Remember that from the last class? Maybe I try to go back to that probability distribution.
So if it suddenly goes towards the opposite direction, then the spin-on will destroy.
Yes, that's true. That's true, because we also have to have momentum conservation, and but not necessarily. But there's always the quantum fluctuations in the system, the quantum uncertainties that we can have on top of that. So it's not that simple. So remember, this was the probability distribution for a single particle on a lattice, and for longer times it looked like this, and what we get for the whole is exactly the same thing. So I have to go fast forward again. Sorry, it takes me. Let me jump out of this for a second. One moment, I'll be back to jump to the right point of the talk again. Okay, let me share this window again. Okay, so now you should see that again. Get my chat window again. One moment. Okay, here you go. So yes, you cannot even say whether it moves left or right. It moves in both directions, essentially. Yes. So these are just, of course, keep in mind, these are just cartoon pictures of what's going on in the system. But now we're not, actually remember now, the whole is not moving at all. We're not talking about dynamical evolution of the system. We're talking about the ground state of the system, which we introduced holes into. So think of the ground state of the system as something like this. This is the object we're dealing with now. Then nothing is moving here. The whole is, nothing is moving anymore, right? So what I'm now just to explain the phenomena to you, I'm just typically focusing on one of the configurations underlying this many-body state psi to explain the physics, what's going on. But of course, they're equivalent configurations, and the actual state of the system is a superposition of these configurations. But yes, so you're getting at important points. You're seeing that the explanation is more complex, but I'm trying to keep it as simple as I can for you to understand the data. Yeah, so there's another good question. Why the spinon data does not show interference, only a single peak? Yes, a very good question. This is because the temperature in our system is not low enough to see this interference structure. So remember, somebody yesterday asked what happens to this interference structure if you couple it to a bath, to a thermal bath. Then I told you that interference structure would go away. And in heat here, something similar happens if the temperature is larger than this exchange energy, then, or in the order of the exchange energy, then this nice interference structure is washed out. Okay, so the temperature is in a regime where it's much smaller than the tunneling, because there we saw the nice interference pattern, but it's on the order of or only slightly less than the exchange energy scale. So there, these interference structures are a little bit washed out. Very good question. Okay, but now let's go back to the ground state and let's try to understand how this dynamical spin charge separation occurs in the ground state. And let me show you the data of this really happening in the system. So here I'm now plotting this. Let me walk you slowly through the data. So I'm plotting this spin hole spin correlator again now. So we're asking again, how is the spin on side I correlated with the spin on side I plus D? Okay, this is a spin-spin correlator. How are these two spins correlated? Conditioned on having a hole at site S. Now there are two possibilities this S can take. So the hole can be outside of the two spins we're correlating. So S can be larger than D. That would be this configuration. So if the hole is outside of the two spins. And then of course I would just see my standard antiferromagnetic ordering up, down, up, down, up, down in my correlation function of these two spins. Or the hole is between the two spins, then it's over here. Then actually you see that you remember that each time you crossed one of those holes, the parity of your antiferromagnetic ordering is flipped. So the antiferromagnetic correlations should also have flipped in this 3-point correlator. And this is what you see here. So this is the distance of the two spins we're correlating, D. Distance where the hole is. If S is smaller than D, then we're in this sector here. Then we're in this situation. If S is larger than D, then we're in this situation, and we have in this configuration here. Now let's go to this configuration first, and you see actually if the hole is outside of the two spins we're correlating, then we have this nice down, up, down, up, down, up, down, up antiferromagnetic correlator. But now you see if the hole moves between the two spins, then everywhere where you had red turns to blue, and where you had blue turns to red. So you can directly see how this parity of the antiferromagnetic ordering has shifted. I can actually show you this even better if I take out this antiferromagnetic ordering, this staggering -1 to the D, this up, down, and I just plot the parity now of the antiferromagnet to the left or to the right of the hole. And here you can see we get one type of parity if the hole is outside of that region, and we get another type of parity for the antiferromagnetic ordering if the hole is between the two spins that we're seeing. So we can directly see this spin flip in the parity, this non-local manifestation of this individual hole that's affecting our entire many-body system. Okay, now that okay, let me maybe stop here for a second. Any questions what the single hole is doing? Because now we're going to take it up and ask what do many holes actually do in the system. And you will see that's actually simple once you understood what a single hole is doing. So now we're going to do the same thing for many holes. So remember, a single hole is like a domain wall for the antiferromagnet. Any questions on this? Everybody fine with that? Okay, then let's try ourselves what happens with many holes. So now the same system, I just have many holes. And if you look at this system and with many holes, you actually see, well, actually the same thing happens as for a single hole. Each time there's a hole, the parity of the corresponding antiferromagnet flips in sign by -1. So from +1, we go to -1 parity, we go again back to +1 parity, we cross another hole, we cross another hole, we go back to -1 parity. Each time we cross a hole, the parity of this antiferromagnetic ordering flips, okay? And if you look a little bit closer at this image, you actually see, well, that's interesting because if I could remove the holes from the system, if I could squeeze out these holes and compress the system together to get rid of the holes, then you see actually you have a nice antiferromagnet because you have down, up, down, up, down, up, down, up. You have a beautiful antiferromagnet back again that you see in this fictitious space that we call squeezed space, because we remove the holes from the system, and in the squeezed space, we nicely recover the antiferromagnetic ordering of the system again. But we can only see it in the squeeze space. Why? Because imagine I want to know how is this spin correlated with this spin. Well, this will depend on the number of holes we have in between. And if this number of holes is not fixed, but fluctuates from shot to shot, sometimes you have one hole, sometimes you have two holes, sometimes you have three holes. So this will flip the spin over here. And if you correlate those two spins under the fluctuating number of holes in the system, you will get a completely random result. There's another way we can take care of what the holes do is by introducing a so-called non-local correlator, this string correlator, which tries to predict how is this spin ordered relative to this spin. And if we wouldn't know anything, the result would be 0 because we have this fluctuating number of holes. But if we can take into account that if there's a hole that the parity flips by -1, then we can take that into account maybe, and this is what this function here in between does. So in the string correlator, actually this operator in the middle, it just counts how many holes there are in between those two spins and accounts for the -1 phase factors that we get in those two holes. So let me put this into context actually just in the remaining 10 minutes now, how this connects to the phases, order parameters and phases of matter that you might know so far. So far, I think you probably have been taught in your condensed matter or statistical physics courses that we have different order parameters for phases of matter. And in this traditional Landau paradigm of phase transitions, we typically characterize the order parameter by some operator A, which we look at how it correlates at 2 points in space. And if we take the distance between those 2 points in space to infinity, and this correlator assumes a constant value, then we say this is a good order parameter for the phase of matter that we're characterizing. Let me give you a few examples to make this more concrete. So imagine you have a ferromagnet, okay? And then of course the magnetization of the ferromagnet is the order parameter, because if we have a ferromagnet where all spins are aligned, if you tell me locally what the spin is doing here, in which direction it's pointing, I will be able to take this local knowledge and predict what the spin is going to do anywhere else in the system, okay? Because we know the spins are aligned. So if you know the spin points up here, you know anywhere else on the chain, the spin will also be pointing up. Same for an perfect antiferromagnet. If you know you have this up, down, up, down, up, down ordering, if you tell me this spin is up, I will be able to tell you what the spin 100 sites away is going to be oriented like, if I have this perfect up, down ordering. Or take a BC condensate wave function. You tell me the amplitude and phase of the condensate wave function at one point in space, and I can perfectly predict to you what the phase and amplitude of the wave function at some other point in space is going to be like. Same for a BCS superconductor. These are all examples of so-called local order parameters, because the local knowledge of the system allows you to predict what's going to happen anywhere else in the system. That's why we speak of these as local order parameters. Now, what people have learned in the past 20, 30 years is that there's a much more general classification scheme for phases of matter that is not based on this Landau paradigm, but which can be extended by this, for example, in one dimension by these so-called string correlators. Yeah? So there you want to know how these two, how this operator correlates at points x and y. But in order for this to go to a constant value, you actually need to know what's happening in between those 2 points in space to predict what this correlator is going to be. So you not only need to know what's happening on x and y, you need to know what's happening on all the points between x and y also to predict a certain outcome. So this is different from a local order parameter, because now it's not sufficient to know what's happening at x or at y. You need to know what's happening everywhere in the system. So you really need a global microscopic view on your many-body state to be able to evaluate this correlation function. Yes, and our correlator here that I showed you here in this string correlator is a very good example of that, because if you just know the spin points up here, you cannot predict what the spin is going to do over here if you don't know how many holes there were in between. Because remember, each time there's a hole, this parity will be flipped by plus or minus 1, right? So you need to know how many holes were in between. So you need to know not only the local thing that's happening here, but you need the global view of the wave function, and this operator actually takes that into account. So these non-local correlators are very powerful. They really allow us to predict new phenomena in condensed matter physics, new types of orderings which we could not predict it before, which do not fall into this standard Landau classification scheme. So here's now an example. Let me show you that, can say a lot, but let's look at data, what data says to this. So let's look at this one-dimensional chain, and let's put many holes into it, 30%, 50%, 80% number of holes into the chain. And let's look at the spin-spin correlation function. So if there's no hole in between the spins, the distance is 1, so the spins are right next to each other, they will of course align antiferromagnetically. But if they're now, the distance is larger than 1, then you see from the experiment, we're not seeing anything. It gives us a 0 expectation value for the correlation function, because we have this fluctuating number of holes, because we cannot predict from this local knowledge of the spin what the other one is going to do. But if I now include my knowledge of the holes, where the holes are in the system, and go back to the string correlator and now include the position of the holes and how they flip the parity of the antiferromagnet, then you see how you beautifully recover the antiferromagnetic ordering in the system, how you can reveal this so-called hidden order parameter now directly in the experiment. So this is very important. You are now able to measure with these quantum simulators hidden order parameters that you simply have no access to in standard condensed matter experiments. Okay, I will jump over the Haldane phase. I'll just keep it in the notes. It's another example of the same kind of physics that occurs. I just want to briefly at the end, just very briefly show you how life is. We talked a lot about 1D. I want to show you actually how life in 2D is very different, and at least give you a flavor of why it's different in 2D. So again, the question we're asking is the same question. We want to understand, how does a single hole behave now in a two-dimensional antiferromagnet? And this is actually a very tricky question, very difficult. Actually, just to show you that it is difficult, I found this nice paper from 1989 from Charlie Kane, Patrick Lee, and Nick Reed, some of the 3 greatest condensed matter physicists of our days that actually worked on this kind of Gedanken experiment. Now, why is this different? So let's imagine I have a two-dimensional antiferromagnet, which I sketch here, and I put a hole, or equivalently, what we like to do more in the experiment is put a doubly occupied site. And now again, you have this competition between kinetic and magnetic energy. The doublon or the hole, actually what they want to do is delocalize, but the spins want to align antiferromagnetically. But now look how this situation is very different from 1D. Let's move the doublon. If we move the doublon, if this spin up hops over here and leaves behind this spin down here, so the doublon is moved, it is delocalized, it has minimized kinetic energy, then it will leave behind a trace of ferromagnetically aligned spins. That's not good because that costs magnetic energy, because remember, you have an antiferromagnetic Heisenberg model. If you move more, let's have this doublon move more or less, so this spin down hops over here, so the doublon has moved again. Now you have even more flipped spins left behind. So you see in big contrast to 1D, where the hole or the doublon can move arbitrarily far from the spinon, here this is not the case in 2D. The more you move away, the more energy cost in magnetic energy you leave behind. So the further you move, the more this costs you in magnetic energy. So you don't have this phenomena of deconfinement or spin charge fractionalization, but you have something else in 2D. And what you have in 2D is actually a so-called polaron that forms around this impurity. So around this impurity, you have now a bubble of modified spin correlations in the system. And within this modified spin correlations, the impurity can delocalize a bit, so it can minimize the energy a little bit, but not over the entire system. But that would cost too much magnetic energy cost, so it does it only over a finite range of the system. And so what you actually get in this configuration is a so-called magnetic polaron, a distorted spin environment around this single impurity that you see. And I just want to show you some data that we can really measure, take photos now of this single impurity, of this new quasi-particle that emerges in 2D. Here's the doublon, the mobile doublon that we take a photo of, and you can see how in the vicinity of this doublon, the spin correlations are actually distorted relative to the background. This becomes even clearer if you look at, for example, diagonal spin correlations. In the vicinity of the impurity, you have this very, very strongly modified spin correlations. They can even completely change sign, showing you the dramatic modifications that the single dopant now does in the many-body system. All right, I think I'm pretty much at the end. There's more to say, but I want to leave some questions open also for some time also for questions. So, but let me, before I leave you with that, I want to give credit to the people who did the experiments in the lab. So let me quickly go here again. So, yes, so on the Fermi experiment that I talked about a lot, that was Jaya's PhD thesis was the spin charge separation I talked about. Yanis did the polaron experiments, and Dominic and Sarah are the new PhD students. Mim and Guillaume were postdocs in the experiment, and Christian Ghosh led that team. On the rubidium experiment, the bosonic quantum gas microscope, the team was also led by Christian Ghosh, and Tony, Simon, and David are the PhD students, and June was the postdoc who now left for a position in Shanghai. And yeah, with that, thanks a lot for listening. I hope you found it interesting and you got a little bit of the physics that we can study in these optical lattices, in these quantum simulators, you know, working our way up from simple problems, single particle problems, to some of the most complex things we are actually doing now in the lab. I just wanted to give you a little bit of the flavor, and maybe now you're motivated to read more on this and learn more about these phenomena. Thanks a lot for your attention.
Thank you very much. Questions and comments?
Hello, sir. I have a question. So this one dimension, when we are shifting from one dimension to two dimension chain, so suddenly that delocalized hole becomes a localized. I mean, because the magnetic energy should be minimized. So just changing the dimension, why this is happening?
Sorry, why, the last question, please. This is the last sentence.
So just changing the dimension, just from one dimension to two dimension, I mean, why that delocalized hole becomes a localized? I mean,
yes, well, that's that's the fundamental change. What happens when you go from 1D to 2D? That's really dramatically different physics. So you think it should be similar, but indeed it's completely different physics. And of course you try to, because in the 1D case, there's the hole can move away from the spinon and there's no energy cost for it to do that. So the more the hole moves, it can separate from the spinon as far as it wants. It doesn't cost more energy to do that. But in 2D already, this is different. This is dramatically different. The more the hole moves, the more magnetic energy cost it leaves behind, as you correctly say. So the physics is entirely different in 1D and 2D for the two situations. If you ask me why, well, that's why, right? I mean, that's but it is striking that there's such a huge difference of these two phenomena.
Yes.
There is one more question.
Yes.
Minal Kanti Giri, do you like to ask yourself directly? Then unmute and ask. Okay, then I can read. The single particle motion and whole motion is same, but in presence of magnetic field, particle motions and whole motion will remain same.
Yes, so that's of course correct. Then we will have effectively, well, remember for us, we're dealing with neutral atoms. So there's no Lorentz force on our neutral atoms, right? They are not charged. So that's a huge difference from electrons. But if we would do this with electrons and remove an electron and create an effectively positively charged hole, it would of course move in the opposite direction. You would have different type of physics. That's completely correct. So we can mimic the behavior of magnetic fields, the Lorentz force, by some tricks, by engineering our lattices to carry some phase shifts when you hop from one side to the next. So basically what you're trying to mimic with that is the Aronoff-Bohm phase shift that you pick up for a charged particle in a real magnetic field. You try to mimic by having kind of a laser-induced hopping with phase factors on our lattices. Yes, indeed, by this laser-assisted hopping. That's precisely correct.
So there is one more question. Is there any speed limit for the ballistic propagation in 1D, or can it be arbitrarily large?
Yes, very good question. So indeed, it cannot be arbitrarily large. It's bounded, and you already know the answer to what the maximum velocity is. So what do you think? Actually, what is, if I give you let me ask like this. If I give you a dispersion relation, how do you calculate the velocity of the wave packet? If I give you a certain dispersion relation. So the connection between energy and momentum. How do you calculate from this dispersion relation the wave packet, the velocity? Anybody know? Taking the derivative, exactly the omega decay. And now if you do this for the band, for the single band that I showed you, the dispersion relation is not parabolic like for a particle in free space, but it's cosinusoidal. Okay, so for a free particle, you know, E is proportional to k squared, to p squared. But in a lattice, actually, we have E is proportional to cosine Ka. Okay, and there's a maximum velocity. If you take the derivative, you will see there's a maximum velocity exactly in the middle of the band for a Bloch wave vector of pi over 2a. And that basically, that maximum velocity is tunneling matrix elements times lattice constant divided by h bar, Ta divided by h bar. So it's proportional to the tunneling matrix element, as we saw, as we intuitively also would have guessed. You know, the higher the tunneling matrix, the faster the particle moves. So there's indeed an upper limit, and the maximum velocity is this just, I think, 2Ta divided by h bar. I have to do the calculation, but this is how you would do it.
There is one question from Noah Van Horn. So Noah, can you ask yourself directly?
Yes, sure.
You can unmute and ask.
Yes, so the question is, you showed that from the Hubbard model, you could then produce a Heisenberg exchange interaction. And then we went on to see many really fantastic things that you could reproduce in the atoms and optical lattices with that interaction, ferromagnetic or anti-ferromagnetic and so on. So I was wondering if you think other other types of interactions could also be reproduced, such as the Jeller-Simski-Maria interaction, which instead of producing ferromagnetic or anti-ferromagnetic alignment, produces a, I guess, perpendicular alignment. So the energy is minimized for the cross product, and then tends to create spirals of this.
Yes. Yeah, this one might be a bit more tricky, although maybe with some spin-orbit interaction, you can realize something like that also. What is more natural for us to do is actually change the anisotropy of the spin model. So we can quite naturally, by using fresh path resonances, go away from the Heisenberg point to different XXZ models. You know, so that's quite natural for us to do actually in the experiment. With the Maria interaction, I don't know exactly. I think there might be some possibilities with spin-orbit coupling, but I would have to look. I have to see again. There might have been proposals for that, but we didn't do that in the experiment.
Any other question? I don't see any more question in the chat box. So I have a general question. This spin charge separation in 1D, does it happen only in the limit of tight binding approximation and strong interaction limit?
I don't think tight binding is so crucial for it, but it's certainly something that only occurs in the strong interaction limit. Yes, so that's true. But I don't think tight binding is absolutely necessary for it. Yes.
So if there is no more question, let us thank very excellent and pedagogical, and I am sure many students have learned many new things, and students have acquired some knowledge about the state-of-the-art experimental physics from one of the leading experimentalists of the world. So with this, I thank you, all of you, for attending this lecture, and especially many thanks to Professor Bloch for giving this talk and for your time. Thanks you very much.
And I will send you the slides so you can have a look at the slides. There's a bit more information also in the slides. Okay?
Okay.
Thanks, everybody. Have a nice day. Bye.
So the next talk will begin at 4:15, about 14 minutes later. And so till then we have break, and see you again after a few minutes. Sourav, we'll be chairing the next session.
Manush Mukherjee.
Manush. Oh.
And speaker. Yeah,
I'm here.
Oh, Manush.
So you have
speaker is also.
Yeah,
Professor Tom is also.
Jonathan is there.
But you just have to ensure the students are here as well.
They will be joining, I think.
But you guys should certainly take a break. Yeah.
Yeah, I'll just.
So how is the situation in Switzerland with respect to COVID?
The situation is, I guess, that we're about quarter vaccinated. like with first vaccines, I should say, but the rates are dropping pretty fast already, and I couldn't tell you why that is. Yeah, we were sort of in the middle of, if you like, we had a rise because of the British variant being a bit more vigorous, and then things coming back. Even though we're opening up, things are reducing. Yeah, so it feels a bit strange, right? I mean, but I think maybe that's a bit tracking, and it's also, I mean, when I look at the people they've vaccinated, it's primarily the vulnerable people, so the hospitalization rates and things are also coming down. So yeah, I think things are continuing on that basis to open up. Of course, the variant that you guys have is probably the primary concern because it seems to spread even faster than the British one at the moment, right?
That's true. That's true.
So,
that's
probably the fear that they have, but the vaccination is going very fast now. So they did, like, our population's what, 8 million. They did 500,000 people last week with a jab. So it's quite impressive, I think, how quickly that's going.
Yeah.
Yeah.
And that's the good side of things.
Yes. Yeah. We have to keep our fingers crossed, of course. We're like, here is mostly Pfizer and Moderna because of the way access was, if you like, and the way the purchasing. And of course, I think there's no good evidence of how these different variants affect the different countered by the different vaccines. So we have to see.
That's right. That's right. There's some studies now happening, I guess. It's all a matter of data.
That's right. Yeah.
Yeah.
So
I mean, the latest one was Pfizer was showing very, very good numbers, right?
Okay. Yeah. I mean, then I think the numbers that I've seen for Swiss Pfizer are extremely good, better than even than the 95% that.
Right.
Yeah. So in that sense.
Yeah.
But I mean, you guys are still really in crisis point. Is my reading?
So I am in Singapore.
Okay.
But here the situation is still very good.
Mm-hmm.
In India, situation is maybe getting a little bit more stable or flattened out. Let's put it like this.
Okay.
Probably the peak has reached for the second.
Yeah.
But no one knows. I mean, because it's I mean, it's many Switzerlands together, right?
Yeah, right. It's a lot of people, and I guess it's
and it's also diverse. So some places are picking up, some places are going down. So it's a little bit inhomogeneous. Yeah.
Yeah. But I guess you can. I don't know how true it is that you can stop, or the government tried to stop people moving between different regions and things like that. But...
Right. That's let's see. This has started happening probably since last week.
Mm-hmm.
So after that, things are kind of flattening out.
Yes,
but I would say still the death is very, very high. I mean, high in the sense, not in percentage, but in numbers.
Yeah. Well, fingers crossed that things get better.
Yeah, right. That's, the more it transmits, the more it mutates. That's the problem. Yeah.
Yes, indeed. Right. Yeah, that's right. Yeah.
So I guess you would be more talking today about the Rydbergs, right?
No, I'm going to talk about penning traps today.
The penning trap. Yeah, right.
Marcus Henrik is the Rydbergs.
Right. Yeah. No. There were too many Rydbergs, both on neutral and ions.
Imagine, yes, right. Hot topic. Yes, that's right.
Yes. So are you starting this penning trap work, or I mean, I remember there was this proposal from way back from Winter Wets group, and on the planet trap with electrons. Is this something you're pursuing?
We actually started by thinking about that, and the thing. I mean, there you sort of have to deal with the fact that you tend to have large orbits. At least to start with, and then you have to sort of, in those sort of traps, you have to wait for these to ring down rather, because you damp them through the electrode. And then the ones were things like anharmonicity, etc. Right? So the attraction of the electron is nice in the sense the interactions would be very fast, but in studying the electron, we thought technologically it looked hard, so we actually then somehow happened upon the fact that we could also do this with just normal ions and lasers, right?
Okay, yeah. I see. Mm-hmm.
And it relaxes some of, or we think it's going to relax some of those requirements, right? Because you can naturally get atoms cold sort of thing and at lower orbits. And so then we came up with a whole proposal for doing quantum simulation and quantum computing, which I'll cover a little bit at the end of this talk, if you like, in sort of micro trap arrays, but with penning traps. And I guess for me, people are starting to make micro trap arrays for RF traps, but to me, the penning traps just got this great advantage. You don't have to put RF through the electrodes. And
that's true, but you have complicated motions, right?
Well, that's the thing. So I think what we really, indeed, the one thing that's problematic is that the magnetron is this inverted harmonic oscillator.
Right.
So then you have to apply additional oscillating fields essentially to cool that.
Right.
Actually, it's, those fields are basically the fields you would apply for an RF trap, except maybe 100 times lower voltage. So in that sense, then to me, it doesn't look too problematic. I think, though, that said, probably our main challenge is how to load these traps, right? The thing that worries me is whether we can load them. Yeah. So we're building a setup to do that. Yeah.
So is this there was some work done, quite substantial, I would say, from Richard Thompson, right?
Yeah, and they were doing stuff in a big trap, and they also did stuff on planar traps, but very big planar traps, if you like.
Right. Yeah. And your line of thoughts is along that, or?
Well, I think the difference in our line of thought is that every ion should sit in its own quadrupole potential, and we would use microfabricated traps. So I think that's a big difference of what we're doing. And in a sense, it came as an accident. I had a postdoc who was thinking about faculty applications, and he did micro traps with me, and he did highly charged penning trap experiments with Gunther Werth, actually, for his PhD. And then we were sort of brainstorming on what he could propose, actually, right? And his background then fitted this area. And I think there are some really significant advantages to penning traps in the sort of scaling up of quantum computing. So I think I'm quite...
So who is this? Maybe I know him. I mean,
this was Joseba Alonso.
Ah, I see. Okay.
He's actually now working leading an MRI group in Spain, but he was,
Yeah, my PhD was in penning traps before. Yeah. So in the with Jürgen Kluge.
Okay.
That's in GSI.
Mass spectrometry or
mass spectrometry.
Yeah. Okay.
But it's all the same, let's say, family.
Yeah. So you'll be able to pick me up on all my mistakes about penning traps in the next talk. No, because I've actually been learning about it more recently and trying to. I'll point out in the talk, there's some interesting things like there's a regime we might operate our traps where actually the magnetron and cyclotron sit quite close to each other.
Ah, okay.
And that's, of course, not something anybody really tried to do, right? Because
right.
Control frequencies, but somehow there you get a very large 0-point motion. And I was trying to then understand this better, and that sort of sent me chasing a lot of things about penning traps, if you like.
I see.
Of it now, but I find that
intriguing
to think about why do you get, basically you get 0-point motion that's not got a dependence of 1 over the frequency of your oscillator. That's sort of non-standard. It's not what you get in a normal oscillator, and then I was sort of fighting to understand where that can come from, sort of thing. That was
yeah. But I guess the electron would give you the advantage of that you don't need lasers, just to wait and it gets cooled. Yeah.
That's right. If you were prepared to have a dill fridge, yeah.
Right.
But then you, like the thing you struggle with there, of course, you have readout of the axial motion. Can you do that fast, and can you combine it with fast control? I think these were all the things we slightly struggled to map out. Like we would say, yes, you need a cavity to do the cooling or a resonant circuit to do the cooling. Yeah. And then you found you wanted another resonant circuit to somehow enhance the interactions, the state-dependent forces, if you like, that you might get.
Right.
So all of that became rather complicated in terms of thinking it out. And
for the electron, it's always the shifting of the goalpost from one problem to the other, right?
Yeah, exactly.
You shift it to the lasers and other.
Yeah, right. We shifted into the lasers because we know that area. I guess that's the deal.
Right.
But yeah, I mean, the detection that laser-driven ions give you is really a special thing, right? In terms of the
That's right. I think there is also some work in that direction. I keep forgetting the names, but I think it's also in UK now. Also started with Wintervet, moved to UK. He has his group now.
Yeah, it's what's his name in Sussex?
Yeah, right.
Yeah, there's a guy doing planar, I think, electron penning traps in Sussex.
Yes.
And I guess their worries again is like about all these anharmonicity issues. And we somehow are taking the approach that probably, like, we will load a smaller fraction of atoms, if you like, that are coming through as ions, but at the same time, the fraction we load should be similar to what you get in small Paul traps too. So I don't think it should be too much worse than that.
I don't know. I mean, at some point, Ferdinand had Pavel Bushev doing started in Ulm, but I don't think he's continuing anymore.
No, he sort of took over Gunter Vet.
Right.
But I never saw any.
Yeah.
If you like, and I think he's not doing it.
No, but even before, I think in Ulm he started with Pavel Bushev, who was a postdoc with him, and I think they started a little bit on that, but then probably gave it up.
Yeah, I think they did some calculations, and I didn't really see any experiment come out.
Yeah, true. Okay, I think we are getting close, so maybe in 4 minutes or so.
I'll try and share my screen. Then that will play. And you see my screen?
Yes, I do. Yeah. This is calcium?
These are John Bollinger's ions.
Yeah. This is the famous science paper, no?
Yeah, one of them probably prior to that, but I was happy to get slides from him and from Pavel Herner, who worked in the Imperial group.
Yeah, I've seen this picture. Yeah. It's impressive. Yeah.
I agree. Yeah.
So we give a couple of minutes before we start, right?
Okay, can I might just pop to the bathroom then?
Yeah, please. Sourav, are you around?
Yes.
Yeah, so is it okay if I make announcement before, to see that the student number should be higher?
Yeah, you can. You want to make an announcement too?
Yeah. So I guess it's open to the students who are already plugged in right now. So maybe it's just I would request you to kind of tell your friends that this is one type of opportunity, that you have really impressive list of speakers, and the diversity of AMO you can actually catch in this lecture series. So please urge your friends to be in all lectures as much as possible. I know it's difficult time, but this is an opening which you can exploit to change your mind. So it's all for the younger colleagues who are working in this field or who wants to get into the field. This is really one-time opportunity. So we will start once Professor Jonathan is back.
Good.
Manas, you can start.
Yeah, I'm waiting for Jonathan to be back.
I'm back. Yeah.
Ah, perfect. Okay, so let's welcome Professor Jonathan Holm from ETH Zurich for this. This is a very different topic from what you have been learning so far, right? And this is trapping charged particles with both electric and magnetic fields. And for me, it is particularly very relaxing to hear more about what I knew maybe 10, 15 years back or used to work on that. And the field has progressed quite a lot. And I guess Jonathan will tell you much more in depth with penning traps and what they're good for, and particularly also in terms of application. Please, the floor is yours.
Okay, thanks very much for the intro. Indeed, this is a different topic. I discussed with the other ion trap lectures of the course before we gave our lectures, if you like, and I very much felt we've started a project on these penning traps, and I very much felt that this is an area that should be of interest and complete a picture of any ion trap physics. Most of the quantum control experiments that you see in trapped ions today, and most of the groups work on Paul traps, so radio frequency fields are used to confine the ions. Penning traps are different. They offer different opportunities and they offer different constraints. And so I wanted to share some of the really nice physics that's gone on in them over the last even decades. Okay, so this is illustrated, if you like, by something that's very hard to achieve in an RF Paul trap, which is this picture that you see here from John Bollinger's group at NIST in Boulder. What you see is really this, these are all individual atoms, right? These are essentially beryllium ions, right? And you see this beautiful two-dimensional crystal of ions on this triangular lattice. And John does these very nice quantum simulation type experiments where he uses this interacting triangular lattice to develop spin models and explore the physics of that. That's just one aspect where this is something which is still in the future, really, for Paul traps, but where penning traps have been very strong, producing nice two-dimensional crystals. So we should start by asking what is a penning trap? And in fact, the first part of the talk will tell you about that, because it's, I think, or I personally find it non-trivial to think about penning traps. I'll tell you why that is in a moment, but let's just think why we need them. So you will have encountered previously in the set of lectures on ions that when you have a single charge, then Laplace's equation tells that you cannot confine a single charge with static fields. And that's, you can think of it like this, that two of these curvatures, if they are positive and are confining the particle in those two dimensions, you have to have anti-confinement in the other dimension, right? So the ion will roll off down the hill and be lost. And there's two ways that you can think of to solve this problem. So the one that you've probably dealt with up till now in these lectures is to use dynamic fields, and that's called a Paul trap. And I think that's been probably the basis for every talk that you've seen so far. So the solution that I'm going to talk to you about today is different, that we come with static fields, so static electric fields, which will suffer from Laplace's equation problem, if you like, but we supplement that by a homogeneous magnetic field and thus provide the full trapping. So let's think about a simple static field, and in fact, a particularly simple form of penning trap potential. So what you see here is an electric potential in space, which confines particles along the z-axis. But you see this minus sign tells us that there's anti-confinement along the x and y axes. I'm going to refer to them as radial and use their coordinate system with a z-axis and a radial coordinate system in the xy plane. So I've plotted such a potential here, yeah. And the thing that supplements that in the penning trap is a magnetic field which lies along the z-axis, right? So it lies along the confining plane. So I'm kind of going to ignore the axial motion for much of the discussion. And the reason for that is that, in a sense, it's kind of normal, right? What is it? There's a confined harmonic oscillator potential, and we will get a standard harmonic oscillator in that axial direction along this z-axis. So the more complicated thing happens for the radial axes, where you see here anti-confinement, and a charge will fall down this potential hill, except that the magnetic field provides a Lorentz force, right? And the Lorentz force tells you that you get a force which is perpendicular to both the velocity of the atom and to the magnetic field. I just see that. Okay, so what can we think about in those terms? Sorry, I got distracted by the chat slightly. Is that as this particle starts to fall down this potential hill, it will accelerate radially, right? It'll get some radial velocity. And then the Lorentz force, which has to be perpendicular to the field and that velocity, will take you round the magnetic field, right? And it's this which is providing then the confinement in the Penning trap. So what is it that's interesting about Penning traps from the point of view, or by the comparison with Paul traps? There are a number of things, and I'll come back to that a little bit later, which is actually a reason why I'm getting into this game myself. But one of them, which is very clear, is that this now is a system where you have static fields, where both static magnetic and static electric fields. And that sort of, I give you a general notion that these can be extremely stable, and that's one of the major benefits of using Penning traps. The other thing, which I'll focus on later, is that there's no power dissipation in these traps. So you can build Penning traps and you don't have to input power. Apart from, I mean, usually to generate magnetic fields, you do that using current. So if there's any, usually that's done with a superconducting magnet. If there's any dissipation there is a bit of a power requirement. So the primary thing is that the stability is very good in these traps. So where do they feature? Actually, they feature in the history of ion traps pretty strongly. In fact, in the history of laser cooling pretty strongly, because the first laser cooling, Doppler cooling experiments ever done were done in Penning traps. That's this classic paper by Wineland, Walls, and Drulinger. So what's the use of them today? And I just selected out a number of them. Maybe I've missed a few of them, but let me go through. One is in precision measurement. So in particular, tests of fundamental theories such as quantum electrodynamics. And one classic measurement there has been of the G factor of the electron. And I've underlined this line because I'll describe that measurement in a little bit of detail later. They get used in dealing with, as I said, fundamental physics. So one of the classic experiments going on today is the ratio of the proton, or the differences, if you like, between the proton and the antiproton charge to mass ratio. So that's trying to detect whether there's any difference between matter and antimatter, which is a very important question when we look at the large ratio between those two things in our universe. They get used in trying to make antihydrogen. So what you want to do is mix antiprotons with anti-electrons, right? And so you've got traps there you want to store for a very long time. So indeed, Penning traps are used for that. And a classic example is by the Alpha collaboration at CERN. They're heavily used in mass spectrometry as mass filters. And then the other things which are more related to quantum, which I wanted to mention, are quantum simulation with 2D lattices. And you saw already this sort of plane of ions on a 2D lattice at NIST. Yeah. And then I'll tell you at the end how this may move towards, and in fact, Imperial have done experiments over a number of years towards quantum computing. And that's an area that my group is starting to work in now. And I want to show you a little bit about why I think that's interesting. So when we think about motion in a Penning trap, we have to deal with the kinetic energy, the potential energy, and the magnetic term, right? And that magnetic term adds a reasonable amount of complexity that's not sort of in your most basic treatments of mechanics. And that's why I'm going to tell you a little bit more about that today, right? So I've drawn here this Lagrangian of our system in cylindrical coordinates, and that's because we have a natural cylindrical symmetry in this problem. That is, around the magnetic field is symmetric, right? So there's some kinetic energy terms. There's this potential, which you see repels along the radial directions and confines along the z direction. And in addition to that, there's a magnetic field term, which you will see involves the radial coordinate squared and also involves the angular velocity, right? And that's proportional to what we would call the cyclotron motion, the cyclotron frequency, and I realize I haven't quite introduced that. That's basically the magnetic field divided by the mass of, or it's the charge times the magnetic field divided by the mass of the particle that you're using. So one key thing about this Lagrangian is it doesn't depend on the radial coordinate phi, i.e. the angular coordinate, right? And what that means, if you were to write down the Euler-Lagrange equation, so this is where you get your equations of motion, right, is that you would find that there's no dl by d phi term, right? So what that means is that the canonical angular momentum, which is what you find in this term here, doesn't change in time. It's conserved in this system, right? And so if we differentiate this Lagrangian with respect to this velocity, change in velocity, if you like, what we find is that that's got a term coming from the magnetic field, yeah? And it's also got a term coming from the kinetic energy term that we see here. So there's contributions from this canonical to this canonical momentum from the kinetic momentum, but that's different from the canonical momentum by this magnetic field term that we have with this cyclotron frequency. So we can derive also a radial equation of motion. And the structure of that is such that you have the usual second order differential of your radial, of your coordinate, if you like. There's some term here which actually looks roughly like a harmonic oscillator type term, right? We've got some parameter which is positive, delta squared times the radius. That's the sort of harmonic oscillator term. And there's a 1 over r cubed term here. And I just remind you that this canonical momentum is a constant. So you see a constant divided by the coordinate sitting on this right-hand side, right? So what's this parameter that I'm drawing here, which is sort of related to a harmonic oscillator parameter, right? So maybe leads to oscillations, you might think, okay? And that's related to both this cyclotron frequency, i.e. the magnetic field strength, but also how much repulsion you're getting or anti-confinement you're getting from the potential. So this equation doesn't look trivial to solve, but actually is one that does have solutions, okay? And the primary feature of it is that you get motion, or the solutions have two frequency components, and the two frequency components are at this frequency, the cyclotron frequency, which is what you would get if you just had a particle in a magnetic field, plus minus this component, which is due to both the magnetic field and due to the anti-confinement of the trap. And I'll come back to where that's coming from in a moment. So what do we see here? We see that the parameters do have to satisfy this equation in order for delta to be a real quantity, if you like, right? Then we have to have the cyclotron frequency high enough compared to this anti-confinement. And that's some condition that sets the operating parameters for a penning trap. Okay, so what are the motions? What we're looking for then is that there are two types of motion appearing at these two distinct frequencies. And so we could plot trajectories in the 2D space as a function of time. And what you would see, at least in the case where omega plus is much greater than omega minus, you would see something like this, where the magnetic field is coming out of the plane here. And there are two types of rotational motion going on, right? So you can imagine the particle following this trajectory, right? And the two characteristic frequency components here, they lead to two types of motion. One which is shifted from the bare cyclotron frequency. So if you were just in a magnetic field, you would have a circular component from a cyclotron frequency if you had no potential present. And now what you see is that the frequency of that type of motion is modified. It's now a cyclotron frequency shifted by some certain amount, right? There's a plus here, but you'll see that that plus doesn't quite give cyclotron frequency, but is adjusted by the presence of the potential, right? So you get these fast loops, that's this modified cyclotron frequency, and accompanying that you get what many people would call a drift motion, or a magnetron motion, which is a slower frequency. So it's omega c minus this delta parameter, which then is somehow like a drift of this circular motion keeps drifting round and round in space at a much lower rate. Yeah. And so these are the two characteristic motions in penning trap, and they have some reasonably interesting features. So the modified cyclotron is actually less interesting in a certain sense. I mean, it's useful, but less interesting. It's just a harmonic oscillator, okay? And it's, if you quantize that, it has energy levels which are just separated by omega plus, essentially, right? The magnetron is actually a more interesting kettle of fish because it's an inverted harmonic oscillator. That's a weird thing, right? So what does this mean? This means that as you go to higher energy levels, or as you go to lower energies of the magnetron motion, you have larger orbits and it's higher excitations of the magnetron motion, right? So this has weird consequences, right? This means that if you want to get the magnetron to be in its lowest entropy state, the easiest way to do that is usually what you would do in a normal oscillator, is you would cool to the ground state, right? And for the magnetron motion, you have to put energy into the system in order to drive it down to its ground state, essentially, which its ground state is now the highest energy state. The magnetron motion is also inherently energetically unstable, yeah, in the sense that if I sit in this lowest, in the smallest, most confined state of the magnetron motion, I, in principle, have the possibility to go to the n=1 state and the n=2 and get, in a sense, hotter and hotter and hotter and develop a thermal population, which is inverted. And in fact, eventually you would expect the particle to leave the trap, right? So energetically, the magnetron motion doesn't seem confined. But what you have to remember is that the angular momentum in this system has to be conserved. And it's the conservation of angular momentum that prevents the magnetron from naturally leaking down this ladder of states, right? So in order to go down this ladder, angular momentum has to change, essentially. That said, there can be dissipative processes, and if you have dissipation that's sucking energy out of the system, that can produce this sort of behavior where you essentially, in an inverted way, heat up the magnetron and eventually lose it from the trap. So then you have to think, what are the consequences? So it's quasi-stable, essentially due to conservation of angular momentum, and you have to worry about whether you lose these particles, right? But actually what you see is that even for an electron, and that I think this loss goes as 1 over the mass cubed, usually it's coming from essentially radiation due to the fact you've got an accelerating charge, right? And it's already a years-long time scale for an electron, and it's then, yeah, I don't know how many years for a heavier particle like a trapped ion atom's weight, you know, so it's 1,800 times heavier, and this thing goes as 1 over mass cubed. So it's a very dramatic suppression. So in practice, then, these magnetron motions are well confined, yeah? And what we have to deal with in this inverted harmonic oscillator is sometimes that things like laser cooling become non-trivial things to do. Yeah. So yeah, here's then I want to go into the quantum motion in a penning trap. And here now, I don't know why I wrote cylindrical coordinates. Yes, indeed. I will treat it in cylindrical coordinates still, right? So we can think about what the Hamiltonian looks like for this thing. So here is again canonical momentum. Here it's now modified by the vector potential. This is sort of the standard Hamiltonian you'd expect to see if you were doing quantum optics and you were using the optical electric field. You would have the or electromagnetic field you would have coming in here. In the radial motion, and here I just restrict to the radial motion, then it's kind of clear now where this frequency component, this delta, is coming from, right? So what's happened in the expansion of this Hamiltonian, at least in the Coulomb gauge, is that what you find is that there's this additional term coming from the magnetic field, which is quadratic in this radial coordinate, but now has a confining form. It's a plus r squared type term, and it's proportional to the cyclotron frequency squared, right? So in that sense, what you have here in the radial coordinate, these are the radial terms, is a confining harmonic oscillator as long as omega c squared minus 2 omega z squared is positive. But on top of that, you have a term which is proportional to this canonical angular momentum, right? And this is the additional magnetic field term. And if the angular momentum gets large, you can see that these terms are always positive. So you've got essentially a confined oscillator, if you like, but you can start to have negative energy levels. That's going to be associated with the magnetron motion. So you can actually solve this directly without worrying about cyclotron and magnetron motion being separated out in frequency, and look for the energy eigenstates. There's simultaneously eigenstates of the Hamiltonian part, but also of the angular momentum, right? And you see that there are two quantum numbers coming in, one which is the angular momentum quantum number, and one is a radial quantum number. It tells you the number of the nodes in the wave function in the radial coordinate, okay? So essentially, again, quantized levels coming in here, comprised of both an angular momentum component and a radial component. So we can also do the same sort of thing in Cartesian coordinates and look at the Hamiltonian there. And it's sort of useful to do that. In fact, you'll see that the first two terms are pretty much identical. But what you see here is that what the angular momentum term is doing essentially is coupling together the motion in two perpendicular directions, which are x and y, right? And that's this basically the magnetic field contribution, the Lorentz force. Yeah. So you can make a linear transformation. So just there's a new set of coordinates being introduced here, which are combinations of the position in one direction and the momentum in the other direction. I suspect I should have swapped y and x sitting here, if you like. And just to say that this is a position, here's a momentum. And what you see, if you like, if this coordinate is maximized, let's say the q plus, you would see that you would simultaneously somehow want to be maximizing both the position and the velocity in the y direction. So it's somehow, you already see the structure of a circular type motion coming in here in these canonical transformations. So in that case, then this writing just in terms of these new coordinates, if you like, what you find is a sum of two harmonic oscillator terms. They've got the two frequencies that we mentioned before, the modified cyclotron frequency, the magnetron frequency. And the thing to notice is that this one is a harmonic oscillator, a positive harmonic oscillator, but there's a minus sign in this term here, and that's exactly the inverted nature of the magnetron oscillation. Yeah. So the energy eigenstates then are energy eigenstates of both types of motion. So with one type of energy, we get a quantum number for the modified cyclotron motion. With another energy scale, right, which is set by the different frequency, we get the other term n minus. And here we have the 0-point motion essentially coming in. And in the angular momentum, it's just worth pointing out that the angular momentum is also just given by the difference in the quantum numbers between the number of quanta in the modified cyclotron motion and the number of quanta in the magnetron motion. Okay, so that's kind of the basic trapping in a Penning trap. I think the main take-home message is that you've got these two oscillations. One of them is an inverted harmonic oscillator, that's the magnetron. And an important parameter there is this delta parameter, which is the square root of the cyclotron frequency squared minus 2 times the confining frequency squared. And just to notice that that's the thing that pops up in the 0-point energy, right? So the cyclotron as itself does not contribute to the 0-point energy, but only in combination with the anti-confinement. Okay, so now let me come to the first set of experiments that have been done with Penning traps, if you like, or one of the key early Advent experiments that sort of were done. And that's what we call G-2 experiments, and they're very famous. They've been done with a number of the sort of fundamental particles, but the most, I think, probably the most fundamental in terms of when you directly look at it from a student perspective is that of the electron, right? So let me explain the G-2 measurements of the electron. And what you know about the spin G factor of the electron is that it's 2 plus some amount. And this amount comes from quantum electrodynamics, right? That's probably, you knew that it was 2.002 something, something, something. The Dirac theory, if you like, gives you the factor of 2, and then quantum QED gives you, the vacuum corrections give you this additional factor. So how does that manifest itself? If you have a spin of an electron, then you've got a spin flip frequency, which is given by the G factor times the Bohr magneton times the magnetic field divided by h bar, right? And actually that's just this G times half of what we know to be the cyclotron frequency. So in a magnetic field, the bare cyclotron frequency, if you didn't have any potential present, would be cyclotron motion at this EB over m, which is the natural circular motion in a magnetic field. So what do you see of these two things? They're highly related to each other, right? But they are slightly different, right? And what this means is that one can go plotting the structure of the energy levels in terms of both the spin and the cyclotron motion. And that's this is a very detailed diagram. I pulled it from a paper, if you like, but let me just explain it to you. Each of these columns is either the spin being -1/2 or the spin being +1/2. So, and on the left-hand side, I'm plotting the number of quanta in the cyclotron motion. So what you see is that the difference between these different energy levels is basically the cyclotron frequency, though it is slightly modified, and the modification comes from the fact that in a Penning trap, this modification, this VC bar, is the modified cyclotron frequency, not the cyclotron frequency. Yeah, so there's a slight complication coming there already. The difference between n equal to 0 and n equal to 0, but with the spin flipped, is ever so slightly different to that, right? Because it's got this extra factor related to the difference in the G factor, essentially, right? So what do we see? When we take the difference of the spin and cyclotron frequencies and divide it by the bare cyclotron frequency, we see that it gives you the difference between the G factor of the electron and 2, which is exactly what you want to know about quantum electrodynamics. Yeah. And this ratio is a factor which is independent of the magnetic field, because all of these parameters are proportional to the magnetic field. So the field itself drops out. And if you can measure this ratio, then you can measure QED independent of what the magnetic field you use. So this is good because all you have to do here is measure frequencies, and frequency ratios are probably the best determined things that we have in physics. So the classic example would be atomic clocks today, where you compare the essentially a transition frequency in, say, aluminum to aluminum ion to a ytterbium atom. And these are known to sort of 18 or 17 decimal places or so, right? These are really remarkable measurements. Yeah. In these cases here, has to be a measurement of this bare cyclotron frequency and the spin flip frequency. And these measurements are made at the level of 10⁻⁻12 or so, but still it's a remarkable precision you can make in terms of the accuracy. Yeah. So this is the starting point. So what do the experiments look like? So magnetic fields, and this is something that's common to all Penning trap experiments, is that they're at large magnetic fields, right? And these are the sort of magnetic fields, several Tesla, where you need usually a superconducting magnet. And especially for stability, those are very useful things to use. But what you find at that point is that both these spin and cyclotron frequencies for an electron, right, will be around 150 gigahertz. And then the nice thing about 150 gigahertz is, if you like, that if you just cool the system down to about 100 millikelvin, you will find that your system is close to the quantum ground state for these types of motion. So both the spin and cyclotron motion, if they come into thermal equilibrium, you'll find they're in the ground state. Yeah. And then there will be some mechanisms by which excitations do get in, but you can find about what the lifetime of these states will be. And for the cyclotron motion, the lifetime of states is several seconds. For the spin, it's 2 years or so, right? So these are systems which quantum mechanical states live for a long time. Yeah. And just to show you measurements of that, so I'll come back to how this is measured. It's about jumps in the axial frequency, actually. But what the cool thing is the way these measurements are made, they are set up so that if the spin changes its orientation, or if the cyclotron motion changes, you will see a change in the axial frequency, which is sort of the measurement parameter. And it's a quantum non-demolition measurement. So you can, in situ, if you like, watch quanta jump in and out of these types of motion. And here you're just seeing that sort of measurement. So there's over time of 15 seconds or so, here comes the particle, it's in one of its spin states, and then suddenly it hops to another spin state and shifts the axial frequency, and that's what's observed. And here is a more characteristic one that's getting you towards this 4-second time scale. So this is really a fundamental jump from the, I think, from the ground to the excited state. And then the excitation decays again after a few seconds, governed by this 4-second time scale. Yeah. So how is that measurement made? I told you that it has to be made by looking at axial motion. So the deal basically is that these electrons are read out by the currents that they induce in the surrounding in the trap volume. Yeah. And so if you were to see one of these traps, it's a gold structure. It's got segments along the magnetic field axis, which is vertical here. That produces the axial confinement, the radial anti-confinement in the static potentials. But in order to make measurements, what they do is they concentrate on the axial motion, which is at tens of megahertz, and that's much easier to see the currents because this motion is larger, essentially, in amplitude. Yeah. So what they use to make sure that the axial motion can see the radial motion, right, because we want to measure cyclotron frequencies and spin frequencies, is something called this magnetic bottle. Yeah. What they do is create a magnetic field inhomogeneity such that the magnetic field is reduced in this region and is higher in the regions above. Yeah, and the potential that that gives you for a spin of magnetic moment mu is not just now the confinement potential of the electrostatic potential, but also this potential, if you've got a magnetic moment, which is proportional to some curvature of the magnetic field, times the position squared, right? So there's now an additional frequency component to the trap that's coming purely from the magnetic component of your electron. And the magnetic dipole moment can come either from the circular motion of this cyclotron motion, or it can come from the actual spin of the electron itself, right? So what can you think of? You can think of the fact that what this does is it means that as you change the number of quanta in the cyclotron motion or the spin, this is changing the trap frequency that's felt in the axial direction because it modifies this term here, right? And so this is actually number of quanta in the other motion, in the radial motion, but it's telling you about what the frequency will be because the curvature of this potential changes in the axial degree of freedom. So with the results of that, that's basically the techniques that are used. Okay, I won't then go into details of the measurement, but the measurements that can be made of this ratio are better than 10 to the minus 12. And actually, these are the best constraints on alpha, the fine structure constant that we have in physics today, done in these penning traps. And I think it's even better than the theory that can be used to calculate. So the uncertainties at the moment in the theory that's used to sort of estimate what alpha could be based on the measurements is actually larger, I think, than the experimental uncertainties on this ratio. So it's quite a remarkable experiment. Yeah, and you could find more details in this paper from Jerry Gabrielsi's group. Okay, so now that was all about electrons, and electrons are kind of a charge, but then they interact with the outside world, if you like, via currents in the electrode structure. Okay. But what I want to come back to now is into laser cooling, because most of the lectures you've seen were on laser cooled ions, and that's important from the sort of quantum control aspect. So the primary challenge, laser cooling otherwise in penning traps is fairly similar to in any other ion trap, so in a Paul trap. But the main problem for cooling is this magnetron motion, which has got this weird feature of having negative energy, right? It's this inverted harmonic oscillator. And the challenge is that in standard Doppler cooling, right, what you do is you sit with a red detuned laser and you make it preferential, you make a friction force essentially, which extracts energy from the oscillator through the fact that the force is velocity dependent, right? And what you're doing then is extracting kinetic energy. And what that will do for a magnetron motion is it will take you down this ladder of states, right? You go to essentially higher and higher n, and we would consider that as heating the magnetron motion. And somehow that's the opposite of what you want to do. What you want to do is to confine your particle extremely well if you want to use it. So just to point that out, then here's a laser spectrum. I showed you a laser spectrum the other day of an ion in a pull trap, and we saw motional sidebands on the spectrum as well as a carrier. And what you find here, this is actually a cold ion. So the deal is that it's nearly in the ground state of both the magnetron and cyclotron modes. Yeah. So here at the center is actually the carrier transition. And you see the normal situation for the modified cyclotron, that there's a blue sideband, which is at a positive frequency. And there's a red sideband, which has basically disappeared because you're in the ground state, which is sitting at a negative frequency relative to the carrier. But the equivalent thing for the magnetron motion, which is a much lower frequency in this particular case, is that it sits on the opposite side of the carrier. This is the blue sideband, or it would have the antijanes coming Hamiltonian, if you like. And this one here is the red, sort of the equivalent of a red sideband that would, if you like, be used to cool down the motion. It would take you from n equal 1 to n equal 0 if you flip the spin, right? So that everything is reversed because of this negative frequency for this magnetron type motion. So that means that standard Doppler cooling heats you up. So how can you get around this? Well, one of the ways to get around this is to take your laser beam and offset it from the center of the trap. Yeah. And what that means is that now, instead of using the velocity profile of the beam or of the interaction of the ion with the laser light as a function of velocity, if you like, that's what you use for Doppler cooling. An equivalent thing can be done if you have a profile in space. Then you can make sure that the atom prefers to interact with light when it's on one side of its trajectory. You can imagine it going, say, round and round like this, than when it's on the other side of its trajectory, right? So in one case, it's got one type of velocity. In the other case, it's got the opposite velocity, right? And again, this can create the same sort of bias you have in Doppler cooling towards absorbing light when you would reduce the amount of momentum in the motion rather than when you would increase it. So this can be used also for effectively Doppler cooling, this magnetron motion. And it mainly affects the magnetron motion because it's got the larger orbit typically, right? It's a lower frequency of motion. So the challenge with that is that once you get close to cooling limits, to make this type of cooling effective, you need very small orbits, yeah? And what that means is that you actually need quite strong gradients. You need tightly focused laser beams, right? So this is challenging because of the need for tight focusing to get cold. And then you have to position a tightly focused laser beam versus your center of your trap very well. So the other way to do it is actually to use an additional electric field which oscillates, right? Which is applied at exactly the cyclotron frequency. So this now is not the modified cyclotron frequency, it's not the frequency of the mode, but it's rather the bare cyclotron frequency. And what that does, it's got a quadrupole shape, which has got a different symmetry to what we had originally. So remember the anti-confinement we had previously was a minus m times r squared sort of term. So it was symmetric between x and y. And this term now breaks that symmetry. And what that means is it actually can couple the magnetron and cyclotron modes. And if it has the cyclotron frequency itself, it sits at the sum then of both of the frequencies of these bare modes. So it's at the sum basically of the frequency of the magnetron to the frequency of the cyclotron motion. And so you get resonant behaviors which can trade quanta between these two types of motion. What's that going to do? It's going to create hybridized states, if you like, which are superpositions, or energy eigenstates, if you like, which are superpositions of magnetron and cyclotron motion. Yeah? And then that leads to essentially thermalization between the two types of motion. So just to say that they trade energy, right? And here's some plots, if you like, of simulated Doppler cooling performed by my student Shrey Jain as a function of cooling time. And then what you see essentially is that the magnetron here is roughly speaking tracking the cyclotron motion in its number of quanta. Yeah. And so they come essentially into thermal equilibrium. And so by cooling, essentially laser cooling the cyclotron motion, one also ends up cooling the magnetron motion. So at that point, that's probably a good point to have any questions. Does anyone have any questions for me?
I don't see on the chat, but maybe I have a question, right? So so this reminds me, like this is like really coupling the axial to the magnetron or cyclotron motions, right?
Yeah.
Which you could do by.
No, but, sorry, in this case, I'm coupling the two radial motions together. You could also do it by coupling it to the axial motion. Yeah. So
right. In some of these experiments, we used to cut the radially the electrode and then apply RF to couple this.
Yeah.
I would imagine this is doing the same, but now you have the laser to do it. So now, which means the thermal equilibrium of the system is, so all the modes would be at same temperature, if I call it.
That's roughly true, yeah. So I think it depends a bit on how strong this coupling is versus the laser damping frequency, right?
Right.
But essentially, you don't want this to be too strong, but you want it to be strong enough that it provides some mixing. And in the case that it does, then roughly these things come into thermal equilibrium in the sense that they have the same number of quanta. Yeah.
Right, but then if you want to do, let's say, the cyclotron to be a modified cyclotron to be in the ground state for your processing, I don't know what you want to do, but then would it be a problem? Because now you kind of traded off the temperature to be higher.
Yeah, that's probably true. I think what you would say is that the axialization field can be turned on and off because it's an RF drive essentially. So you would, if you wanted to work, you probably want your modes to be close to the Doppler temperature, right? So at that point you turn this on during Doppler cooling, but then you turn it off and you proceed with sideband cooling without the axialization.
Oh, I see.
And at that point, you see, if I look at this diagram here, at that point, then what do you have to do sideband cooling? You have to go and find the red sideband of the cyclotron motion, but then you probably, for the next cycle, go and select out the frequency of the blue, if you like, the positive component of the magnetron, because that's what's going to cool the magnetron. So sideband cooling is resonance selective, and you would jump from one to the other. But Doppler cooling cannot be resonance selective. With Doppler cooling, you kind of plunk your laser on the red side and it couples to the entire red side a bit stronger than it couples to the blue side is usually what you're using. Yeah.
I see. Yeah, I get it. Yeah. Thanks.
Good.
Are there any other questions? Then this is a good time maybe.
Can I ask a very general question? Yes. So you are dealing with two-dimensional harmonic oscillators and they are coupled oscillators. Am I right? If so, you have shown that they can be described in terms of Cartesian coordinates and radial and cylindrical coordinates.
Mm-hmm.
Can you also describe them in terms of Laguerre polynomials?
Yeah, I could maybe just, so maybe I just go back a bit. So of course, once I'm writing down this Hamiltonian, I've gone to a set of coordinates which is uncoupled again, right? So the magnetron and modified cyclotron are uncoupled coordinate sets, yeah? So indeed, X and Y are coupled, but you can choose a parameter set that produces normal modes and are separable, yeah? So when you said Laguerre polynomials, one thing to note about the solutions to this Hamiltonian, right? Is that you have a product, I didn't write it down, the wave function, but you have a product of something that just looks like e to the im phi, which is the usual angular momentum wave functions that you know from hydrogen, if you like. And then these guys here, the solution to this equation is some exponential factor, but includes a Laguerre polynomial in R, yeah? So that was, when you said Laguerre polynomials, it triggered that thought that the lowest energy state, actually, you can kind of see it, or lowest angular momentum, if this was 0 and this was 0, it's very straightforwardly a two-dimensional harmonic oscillator, right? So you would just get a Gaussian. But once the angular momentum increases in its quantum number, you start to, and for higher excited states, it's a two-dimensional problem, you start to then get these Laguerre polynomials appearing for the eigenfunctions. Yeah. So I hope that was sort of what you were asking. I think you're probably on the right track.
Is that okay?
Yes, okay, thank you.
Okay, let's move on then.
Good, okay. So I probably stopped a little bit late, but yeah, okay, good. Good, so I just want to show group results from the Imperial group. So they've sort of been, I think, along with John Bollinger's group, they've been at NIST, they've been working on sideband cooling. I think the Imperial guys, they laser cooled all the radial modes to the ground state, which was sort of a new step for them a few years ago. So I wanted to share with you some of those results, if you like. I got them from Pavel Hermo, who was a PhD student there and will be arriving with me for a postdoc soon. So this is the result of Doppler cooling, yeah. And what they used there was both an offset beam, which I've described with this intensity gradient, and also some axialization, which is the potential that I just described. So what you see, I mean, the frequencies of oscillation here are by ion trapping standards lowish, right? So typically people are working with more than 1 megahertz of trap frequency. And here you see a magnetron motion, which is at 50 kilohertz. Yeah? And the difference between those two means that the sideband structure is actually rather complicated, okay? So here is the sort of set of transitions close to the carrier, yeah? Here's the first sideband of the cyclotron motion. And each of them are somehow decorated with a number of resonances, and that's the all the different sidebands of the magnetron motion, which is very low frequency. So still what's happened here is that though you're thermalized, the temperature of these ions is reasonably high, okay? And so you're all still seeing, if you like, plenty of sidebands. You're not fully in the Lambdicki regime. You're seeing plenty of sidebands and a similar sort of profile of the sidebands for the cyclotron motion to the magnetron motion here, yeah? So anyway, this is the result of Doppler cooling, and what this means if you're outside the Lambdicki regime is that you have to work a little bit harder at the sideband cooling, but nevertheless, and this is the spectrum I showed you earlier, they were able with many cycles of sideband cooling to bring themselves down to the quantum ground state of both of these motions, if you like, the key feature, I think, at least at the level of this lecture, is the fact that these sidebands are reversed and that the ratio of the sidebands, you probably heard from DD Leibfried, gives you the temperature, and you'll see it's about a half there, and there's probably some other limit there. Well, they give the temperatures, so they get down into the ground state for both types of motion. Yeah. So that shows, if you like, that Doppler cooling is possible for these sort of systems. And the main challenge there, I think, is that sort of remains in a certain sense from those experiments is just the very low trap frequencies they're working at. That sort of further complicates the cooling. Okay, from there, then let me talk a little bit about John Bollinger's experiments. Here, I want to tell you a little bit about 2D physics in ion traps. So as I said, you probably heard a little bit from Christian Roos about how they try and make 2D crystals in Paul traps. And the challenge there is to deal with the radio frequency driven motion that we call micromotion. Yeah. So in penning traps, then these beautiful 2D lattices have been produced, and that produces a natural two-dimensional lattice for doing quantum simulation type experiments. And I'll tell you about that in the sort of following slides, if you like. The other aspect where people try to go towards 2D physics in ion traps is actually in microfabricated radio frequency traps, where there's people working on that in a number of different groups. And the key there is not to try and go to a regime where you have ions sitting where there's a larger RF field, but rather provide a quadrupole potential, a static quadrupole potential for each ion individually, but also have an individual radio frequency potential for each ion individual, which is a confining or an oscillating quadrupole, right? So what does this mean? It means making microscopic potentials for each and every ion. And then in order to make ions interact, they have a Coulomb interaction. You basically have to get them close enough together. So in order to do this sort of thing, what you really have, what's opened up this possibility is the possibility to fabricate microfabricated chips with length structures that are where this distance is small enough that that the repulsion between the two ions can produce significant normal mode splitting, which allows you to do the sort of quantum control that we do in ion traps today. Okay, so this people are working on now. There are people with sort of 3 sites, if you like, and they think how to scale this up. It's got some challenges. One is that it requires small traps. So in fact, in order to get things tightly packed, you typically have to bring them close to the surfaces, which is where you get more noise for the motion coming from heating. And it requires for the RF traps, high voltage RF signals applied to these traps, which is a source of heat dissipation. Okay, so I'll return to this. A future project, the thing that we're working on penning traps is actually in this direction to do it with without the high voltage radio frequency. Yeah, but first let me tell you a little bit about these beautiful experiments from John Bollinger's group at NIST. So here's a picture of the electrodes of the NIST trap. So what you see along the magnetic field, that's where you need the confinement, is several electrodes. So these electrodes can be biased such to produce a potential well along that axis and to repel ions in the radial dimension. You see also the central electrode is split up, and I'll tell you why that is in just a second. And this structure is about 2 centimeters in its diameter. Yeah. And the crystals that you'll see are much smaller than that. That's not quite to scale, but can go up to being millimeter scale crystals of atoms. So this is what it really looks like in life, right? It's got these gold electrodes, which are held by Makor spacers. You can see various Kapton wires. And it has to be placed inside a superconducting magnet. So there's this 4.5 Tesla solenoid that he has in his lab. So what's the sort of frequencies that John Bollinger works with? He has this 4.5 Tesla magnet for beryllium ions, okay? So his cyclotron frequency is 8 megahertz or so. His axial frequency is about 1.5 megahertz, and his magnetron frequency, again, by ion trap standards, that's pretty low, is around 160 kilohertz. But what he's doing is working with large crystals of ions, right? And crystals provide a balance between their confining potential and the Coulomb interaction, right? That's how the crystal forms in that sense. It's a naturally forming crystal. But one of the things you have as a tool there is that if this ion crystal is, or these set of ions are spinning around at a certain velocity, then in the magnetic field, that produces a different amount of radial confinement. Yeah. So if the angular momentum is larger, what does that mean? That means there's more outward pressure, if you like. And what that can cause is that at large rotation frequencies, if you like, or at a range of rotation frequencies of the crystals, you get different shapes of ion configurations, which are stable. Yeah. So at the 2 extremes, so as you go towards the cyclotron frequency, or if the crystal comes down towards the magnetron frequency, you get, you can imagine that all of these blobs are drawn as if the magnetic field is pointing upwards. Yeah. So you get them radial planar crystals, but as you go to this cyclotron frequency over 2, then you get a situation where the crystal is much more confined on the axis, and you get, if you like, a pencil type crystal along the axis. Okay. So 2 cases John has used, one where they have the system rotating close to the magnetron frequency, where they get single planes of ions. And I'll show you a bit more of that in a second, how they do that. Here is a top view of the ions, and you see this nice lattice, right, structure. Here's a side view, and you see that it's a flat lattice. It's a 2-dimensional structure. They've also worked in the past with systems which are in an intermediate regime where they form 3-dimensional crystals, right? So these are body-centered cubic crystals with sort of numbers of ions on the sort of 100,000, where they were able to observe this through fluorescence and through Bragg scattering. Yeah. So one of the challenges there is that in a symmetric penning trap, you don't have control over what the rotation frequencies of these ions are. Remember, I said angular momentum is basically they're conserved, right? And so the challenge in working like that is that you might be wanting to work in a regime where you have a 2D crystal, but gradually your ions will get faster and faster through some imperfection in your system.
Jonathan, maybe your Can you hear me? Hello, can you hear me, Jonathan?
In phase with each other. Can you still hear me?
You were sometime not audible. Something happened at your place.
Yeah, my laptop decided to change the speakers on the microphone. I hope you can hear me again. Yeah.
Yeah. Now we can hear you. Yeah. So
okay. So let's do that. Yeah. So you see that these opposing pairs here essentially are in phase, but there's a phase difference at 90 degrees between the different pairs. Yeah. So what that does is it slightly contorts the crystal. It makes it non-circular anymore, right? It provides a definite axis. And then this frequency is oscillating. So this leads to a rotation of a preferred axis as a torque, right? Which spins the crystal around. And the rotation you get is basically the same rotation of this drive frequency here. Yeah. So let me just show you a picture of that. So in their trap, then they can view the ions from the side, right? And this is a side view. So what you see here, you can see probably shells of ions here. This is then a three-dimensional crystal. And then the system gets spun up by the axialization, and a movie should start now. And what you see is that as it gets spun up to the right frequency, then the crystal goes through from 3 to 2 to 1 layers, if you like, and becomes a planar crystal, at which point, looking at the top, you see the nice structures that you saw before of these two-dimensional planar crystals. Yeah. So some of you might notice that there are places here where there are holes in the filling. Yeah. There's two possible reasons for this. One is that atoms, of course, have atomic structure. So atoms can get into electronic states where they don't fluoresce anymore. That's probably not the case here. I think the bigger challenge that these guys sometimes have is slightly imperfect vacuum. And what that leads is sometimes that beryllium collides with hydrogen and forms beryllium hydride atoms. And often what that'll do is that these hydride atoms, these molecules essentially, because they're slightly heavier, they will move to the outside of the crystal. And indeed, you see more of these holes occurring on the outside than you see occurring in the middle of the crystal. Yeah, so that's an additional detail. But this basically spinning at the right sort of chosen frequency chooses your angular momentum that you have for your ions, chooses then the radial confinement, and allows you to then produce the right properties of asymmetry between radial and axial to enable you to form these planar crystals.
So what is the scale of this crystal? So how large is this?
Yeah, I had it in another picture, but I don't know, maybe it comes next. I think it's about, like typically these are sort of on the several hundred micron level. So actually I thought I had, yeah, so I think the scale length that I do know comes from these things is that this distance between the atoms is sort of between 15 and 20 microns, if you like. And so, yeah, here you see it. There's a 500 micron crystal. Yeah.
So the laser beam, I believe it's a Gaussian beam, and we see this distribution of the fluorescence rate. Is it related to the laser beam profile, or?
That's a good question. I guess in this case, you see it at the edge, right? And I wouldn't know. I guess here it looks fairly homogeneous, so I think the laser beam must be quite large.
In the other one, the second one.
Yeah, in this other case here, yeah.
No, even the third one, which you just showed now. Where the next
okay, this one here, you mean? Yeah.
One more.
Yeah. This?
Yeah, here. Yeah.
Yeah, I agree with you. They're slightly more intense in the center. Yeah, I wouldn't like to predict that that was the laser beam, but I could guess that that was the case, right? I mean, that's it. Yeah. Yeah. Yeah, I mean, you do in large crystals in Paul traps, you have a different reason for getting that sort of profile, which is that the Doppler are changing with position. But I think in this case, the plane is not oscillating dramatically differently at the sides to in the center. Right. So I think it should be much more about the laser beam profile. Yeah.
Okay, sorry. Yeah, please go ahead.
Yeah, that's good. Yeah. So Sourav says volume is gone. Volume is gone on my speaker. Yeah, good. Thanks for interrupting.
No, now it's fine. Now it's okay.
Yeah, good. Okay. Okay, so I think, and this is probably one of the reasons, there's two reasons probably why people working in quantum information in trapped ions don't naturally work with penning traps, right? One of them you've already seen is the complications of cooling the magnetron motion, but the other is actually atomic structure, right? One thing that happens at high magnetic fields like several Tesla, it's that your splittings are very large, yeah? And so you need to have, beryllium is actually quite convenient in that sense. It doesn't require so many different lasers, right? But if you want to manipulate spin states or qubit states in beryllium, you need to bridge this 124 gigahertz splitting. That's a high and bit painful frequency, both for microwaves, but actually much more so for lasers, yeah? Because what it requires to do things like Raman transitions is that you've got high frequency modulators that can bridge such frequency gaps, and those AOMs will not do that. So typically what you require is multiple laser systems, phase locks between them, et cetera, and in the heavier ions with slightly different structure, this actually just requires lots more lasers, yeah. So in a certain sense, then that's probably one of the challenges, and these are the two challenges that led people towards Paul traps in terms of simplicity, yeah. So nevertheless, beautiful experiments has been done. So let me just mention some of those. So the next thing I want to tell you about then in these experiments is the sort of control of interactions between spins in these experiments. And you've seen the physics of that already if you attended a little bit in my talk on motional states, but also Christian Russer's talks. Yeah? So what you have here is essentially a standing or a traveling standing wave potential. So there's a laser beam. Here's the plane of the ion crystals, if you like. There's a laser beam that comes towards that plane and a laser beam that comes out of that, slightly out of that plane. And those have a difference frequency, which I'll denote by mu, sorry, yeah. So just to give you a scale, right, the wavelength of this standing wave, which moves across the ions at this point, is then about a micron. So this leads to a term, which is this state-dependent force I told you about the other day, right? There's some sort of modulation frequency, but otherwise on any particular spin, there's a spin operator, which is coupled to the axial position of that ion, right? So that's the coupling that gets used. And as you saw, I hope in Christian's talk, then you can derive an effective Hamiltonian for this sort of dynamics in certain limits. So where you get an additional term. You get one term which couples the spin to the motion. But if you go to detunings that are sufficient that these don't play a role, or you pick certain times, then you're left behind with essentially what looks like an interaction term between the spins, an effective interaction via the motional modes. And the interesting thing about these is that the interaction parameters between any two spins in your array can be chosen experimentally, right? So the range of the interactions, the form of this J matrix can be chosen to have different dependencies on the difference in the distance between the ions in the array. And so that dependence is characterized by a power law factor, right? And the key parameter that sets this power law is how far, if you have a common mode of motion at one end of the set of modes that you're using, how far detuned you are out from that common mode tells you what this power will be. Yeah? So typically what happens is that as you go to larger and larger detunings here, you get A increasing. When the detuning only couples to the common mode of motion, that's homogeneous over all of the ions, you get long range couplings equally between all of the ions. So all of the spins couple to each other. But as you start to detune further and further, you go towards a limit, which is dipole-dipole type structure, 1 over, or A is equal to 3, if you like, so 1 over R cubed. Yeah. And indeed, that's the structure that they've mapped out in this system, if you like. So here I've plotted the experimental detunings that are used, and here are the Jij matrix as a function of the separation, if you like. And you see, I think these are probably calculations, actually. You see the different values of this power law. Yeah, so this is long range interactions, all-to-all coupling. This is got shorter range dipole-dipole, and this is still considered long range in a certain sense. So one of the nice experiments that they did there was to look at spin squeezing, which maybe you saw in Vladan Vuletic's talks also, right? So in a sense, these were used as a benchmark for control of these long range interactions. And the basic notion is that the unitary transformation under this interaction set has a term which is proportional to the spin. This is now the total spin of all of the atoms, but here you can think of it as being the sum of the spin terms of all the individual atoms, okay? And then there's this interaction term, which actually just looks like the total spin squared. So what I'm plotting here is sort of Bloch vectors for this large spin vector made up of a sum of all the individual spins, right? And if I just have a standard quantum system, if you like, that I prepared in one state and then rotated with a pi/2 pulse, I get this sort of coherent state type structure on the Bloch sphere, right? It's got equal quadrature amplitude uncertainty in both directions. But this term here, what does it lead to? It leads to, if you're in a plus eigenstate of Sz, then this Sz squared adds to that state, right? Adds extra energy and you'll get faster precession of the state. Whereas if this term is minus, right, then what you will see is that the S squared is still positive, and you'll see that the precession is now slower, if you like, and would be expected to be from here in the opposite direction, but then is slightly accelerated, right? So what do you see? You see a shearing effect on the Bloch vector distribution, right? States that are higher in the total spin, they get moved ahead of states that are lower in this total spin, that are negative, right? And what this does is it stretches out this Bloch vector such that you get, in one direction, you get higher uncertainty. In the other direction, you get reduced uncertainty, and that squeezes the states of the spins below the standard quantum limit. So what can you then do? You can then analyze what this distribution looks like. And here what they're doing is they're changing the angle of essentially how they view the spins. And you can see here they're putting the variance of the spin vector, which is basically the width of this distribution. And you can see that it goes down for some angles before increasing for other angles. And that's the fact that this thing is an oval now. Yeah. And then they also use this to show that they could do sensing at some level, or how this is a function of the amount of time they apply the Hamiltonian for. And what you see is that the variance of this squeezed variance gets reduced to down towards 10 dB reduction in the variance, if you like. And then at some point, the interaction's on for long enough that errors start to dominate and the squeezing isn't good anymore. The other factor that happens here actually is that this thing gets so squeezed that the Bloch vector distribution wraps around the whole distribution, and you start to get all sorts of interference fringes on the backside. So more is going on, but these are the basic signatures of spin squeezing in this system. Okay, finally, I think I have a little time left. Maybe there I just invite any more questions, because I'll move to a slightly different topic at this point. Yeah.
In the chat box, there is nothing, right?
Okay. I'm free to go. Or anyone wants to stick their hand up?
Yeah. So in terms of the spin squeezing, right? So there are other systems where spin squeezing is easier, right, compared to here.
Yeah, I don't know about easier. I think there are certainly in some of the ensembles now, they've probably achieved higher levels of squeezing. Yeah.
Right. So how would, I mean, what makes it different in doing it in penning traps?
What makes it different? I guess in some of those systems, then, like one of the things that you could see about a penning trap, if you like, is that from the pictures of the ions, then these ions are individually recognizable, right? So in a certain sense, the longer perspective is taking advantage of the usual advantages of dealing with ions, that detection can be done very well, and you can see each and every ion typically, right? So in that sense, then I think this, as I said, it here was somehow a benchmark for how good the interactions were. But in a certain sense, it's also the starting point for doing examinations of other spin models. But this was sort of the most natural one to examine to see how well things are working. And of course, what you want to usually start off with quantum systems is sets of interactions where you produce states which are easy to characterize. And of course, squeeze states are somewhat easy to characterize compared to some complicated many-body states. So the signatures are clearer. And it's a good benchmark usually for those sort of systems.
That's right. That's right. There is one question here.
Yeah.
when you describe the inverted harmonic oscillator system, this is from Noah. Is this type of system that is sometimes described using the analogy of a negative temperature, since entropy decreases with increasing energy? Is this analogy useful?
Yeah, I have to think about that. I mean, certainly, I mean, your statement that the entropy is decreasing with increasing energy would be, yeah, I mean, what would I say about that? So, of course, if you're in a single eigenstate, then your entropy doesn't change, right? So it's about it's distributions of states which would contribute to some sort of increase in entropy. And I think what I would be saying about the magnetron is that somehow if you want to produce usually when we try and produce a state which has got zero entropy or is a pure state, the easiest thing to do is to kind of drive to one end, drive dissipatively towards one particular state where the dynamics turns off. And usually the easiest one to pick is the ground state of your motion. You cool and cool and cool, and then there's a natural point below which there is no energy. And in the magnetron motion, that'll happen when you've driven it to the highest energy, actually. Yeah. So now, is there an inverted temperature? I think I always just think of it, what would be the distribution of states? And indeed, if you had what I might call a thermal state for a harmonic oscillator, which would have a larger occupation of n equal to 0, smaller of n equal 1, then you would look like that you had a larger population of a higher energy state. But you kind of have to think also that the Hamiltonian has a reversal in the sign for the magnetron motion. So that's where I wouldn't be too confident in answering your question and saying, yes, this has negative temperature. Yeah. So that's me being less comfortable with that concept without reading about it a bit to check out that I agree with the point. Yeah.
Okay, there is one more question. Can you tell a bit more about why beryllium is easier than maybe calcium in the NIST experiment?
Yeah, okay, I can do that. So laser cooling, well, what Doppler cooling, sorry, I'm trying to find the atomic structure. What Doppler cooling does, right, is what you want to do is you want to have, you want to scatter many photons, right? And so one nice feature of, here's beryllium, right? And one nice feature of beryllium is that if you start in the spin 1/2 ground state and you excite into the MJ spin +3/2 state, the only place that you can possibly decay to in that atom is back to the same state that you started with. And so you need really one laser to do laser cooling. Yeah. And that's good in this, and that's just based on selection rules. And this is good in these circumstances because having another laser that repumps you out of another level means having really a separate laser because the splittings here are so large. Yeah. Now in calcium, what I try and remind you that we had was low-lying D states. So these were D5 halves or D3 halves, and they had a lot of Zeeman substructure. Yeah, and in fact they had larger total angular momentum than the P3 halves here. Yeah. So what that means is that you can't anymore use a selection rule that will just decay into one state in the ground state, but also you can't even tell it to just decay into one of the D states. You have to occupy several. And so what you'll need inevitably to do the cooling is multiple lasers to do repumping. So you just need many laser systems. Now, I think the thing that's starting to look promising about that, and this may be why penning traps becomes more interesting again, is that now you can buy electro-optic modulators which do tens of gigahertz of bandwidth, right? Because you can buy these, well, you can buy them at 1550 for certain, but you can get them actually also in optical domain. So in that sense, then it suddenly starts to become possible in the laser domain to start to think to build systems that can repump calcium. Whereas I think 10 years ago, I would have been a bit doubtful you could do that. But now maybe you don't need tens of lasers just to do the repumping because the modulators got better. Yeah. And so I think at that point, then penning traps become a more feasible prospect again. Also, if you want to, there are, decent ways now to do phase locking at high frequencies. You know, you can get photodiodes with bandwidths of tens of gigahertz now. And again, this just opens up these possibilities that maybe weren't available before. Did that answer your question as well as go beyond it? Yeah.
I guess that's was fine with Nishant. Yeah, so there is thanks. So maybe we can go ahead.
Yeah, great. Okay, so let me just come to quantum computing. So my primary domain has been quantum computing in Paul traps, right? And I just want to tell you about some of the challenges that limit the scaling. And one of the things we have to think of there is that we have beautiful quantum systems and sort of which maybe can go to 100 ions or so. And you've seen in the Penning trap a bit more on that from the ability to go into 2D, right? But we have to bear in mind that quantum computers as a whole will require, if they do error correction, many more ions ultimately, right? So we have to think about scaling. And I don't necessarily think about scaling all the way to 1 million in one go, but we should think about how to go beyond our standard regime. And there are various architectures for doing that. One is holding ions above chip structures and shuttling them around, right? And this is sort of an illustration of that, where you confine ions in smaller numbers together to do high fidelity gates, and then you actually transport these ions around above a chip, yeah, with potentials which are then dynamic, which move the ions around. So what's the challenges of doing that in Paul traps? The standard thing has been to use these radio frequency traps. So there's multiple challenges. One, if you came to the lab, my lab or anyone else's lab, you would find that both the static potentials in a Paul trap, they vary strongly. They're what produce the harmonic confinement. But the RF potential is also producing strong harmonic confinement. That's how we confine the ions, right? And these two things are both microscopic potentials, but they have to be co-aligned with each other. And one of the problems you have is that if any charge distribution changes, then the static potential will change, but the radio frequency will not change, right? And what that leads to is the fact that you move the center of your trap and you start to get driven radio frequency motion, and that's kind of a pain for the laser ion coupling, yeah? So a daily thing that's done in the lab is to line up these potentials. And if you think about doing that in complexity, in large numbers, that seems like a challenge. Yeah? One of the other things that's kind of intrinsic to Laplace's equation again is that the zero of the RF potential is intrinsically a one-dimensional thing. And what you see is that I break that in this chip structure because I have these two-dimensional junctions. And actually, those are quite troublesome in trying to scale up ion trap quantum computing, right? How to deal with the fact that you will have to have large driven RF motion going through junction structures. And then the final one is this heating of these chips. And I think that's best illustrated by this picture from Sandia National Laboratories, where they just look thermally at their trip which is suitable for ion trapping, right? And they see the whole thing is hot, right? And that's really that there's high voltage radio frequencies, sort of tens of volts applied to this chip. And there's some power dissipation and losses in the chip, and that's going to heat the chips up, right? So all of these things make you worry about scaling significantly, and they at least present challenges to that. So this was in a sense where we started. We were thinking to ourselves about a slightly different problem that I already described about making micro traps with ions trapped in neighboring regions where the ions are close enough together that they could interact with each other. And what we spotted, or what we thought, was that doing this with independent RF traps, this problem of aligning the two trap potentials and the problems of heating look troublesome. Yeah. So we asked ourselves the question, why not just deal with microscopic potentials in the static domain and then have this homogeneous magnetic field to do the confinement, right? And this is what the Penning trap offers you to do. Suddenly, instead of having, for 100 ions, 100 different microscopic RF potentials with a null, you just put a homogeneous magnetic field and you do everything in the static domain. So as I said before, the challenge with any of these microtrap approaches is to get the ions close enough together. And that kind of forces you to bring them down towards the surfaces. And this is where noise comes from in ion traps, is heating due to electric field noise on the surfaces. But one of the advantages of the Penning trap there is the fact that everything about your confinement is specified from your static potential and not from a radio frequency potential. So actually what you find if you look at the curvatures of these potentials is that to make a Paul trap stable, you need to use, for a given voltage, you get about 1/16 of the trap, or a quarter of the trap frequency, it's the square root of the curvature, relative to what you get for just a static potential, right? So the penning trap here wins in the sense that if you have a finite voltage you can reach, and you're asking to make an array with a certain spacing, you can get higher trap frequencies for the penning trap relative to what you could ever do for the RF trap, right? So there's a slight win there. It's not the biggest win, but it's a useful one, I think. And so what we find is that for reasonable parameters, we think that these essentially the splittings of the COM and the stretch type motion could be on the level of tens of kilohertz, which is higher than I think is probably possible in Paul traps. Yeah. And one sort of cool thing once you go into 2D is to think about what this means, right? These sort of distances between trap sites, then you only need to have a 1 centimeter by 1 centimeter chip. If it's filled with trap sites, actually you get to fairly significant numbers of ions, right? I don't think we're going to get there in one step by any means, right? But we already make 1 centimeter squared chips. They just aren't covered with trap sites today, right? We couldn't possibly control anything like 250,000 ions. In fact, this project at the moment lives in theory, and we try and load 1 ion maybe in the autumn. Yeah. So the perspective looked interesting to us. I think that's what I wanted to say. So what did we have to do? We had to actually figure out if it's possible, right? So one of the things we did was to look at what the normal modes of motion would be of this system. So in these sort of lattices, you can specify your potential. You can ask where are the ions trapped relative to the centers of the potential, right? And one of those is the circles. And this is us trying to do a hexagonal lattice. We have to then solve these coupled oscillator equations that you saw before for a single ion, but with a Coulomb interaction, it's much more complicated, right? But nevertheless, we came up with a theory for that that could split things into a kinetic energy term, essentially, a magnetic field term, an electric field term, including the Coulomb interaction to solve for these normal modes. Yeah. I won't talk about that. That was a nice result that came from the maths that my student Shane spotted in the theory of all of this. So what are the interactions you get between oscillators at the different sites? So you can think about an ion here and an ion here, and they oscillate in along the axis. That's their axial confinement. And then they have this strange cyclotron and magnetron motion. And who knows what those interactions are going to look like between the two ions and what the normal modes will look like. Yeah. So they have a certain distance, and we can specify that distance relative to the magnetic field vector, right? And so then what we see is terms where we have essentially hopping between different sites. So this was this coupling that leads to mode splitting that I showed you in the last lecture. And basically we find for all the modes that it's got a dipole-dipole type form. And actually what's weird about it is all the dipoles look like they're pointing along the magnetic field, even though the radial motions are going around the magnetic field. In fact, I wasn't aware of this, but if you are aware of this, then you're probably immediately spotted that if you have rotating dipoles in a plane, actually that somehow in the interactions, the moments that come up look like they're oscillating dipoles coming out of the plane. Yeah. So this is what really was going on. But for us, it was a surprise initially. Yeah. So one of the other interesting things about the penning trap is that you've got a splitting frequency, which is proportional essentially to the 0-point motion of the modes squared. Yeah. And in the axial motion, that's perfectly normal. This is what you'd expect for a harmonic oscillator. The 0-point motion is sort of h bar divided by 2m times the frequency of the oscillator, square root. And here you see the frequency of the oscillator appearing. In the penning trap, you've got a slightly strange motion in this radial plane. And what that leads to is actually not the frequency of the mode sitting there, but for both the magnetron and cyclotron motions, you get the difference frequencies of the two modes sitting there. And that's an intriguing feature because even keeping the two frequencies of the modes high, you can make this small, and this makes then interactions large. Right? So this is a new tunable parameter. And I should just say that's not very explored in previous work because nearly everybody worked in a regime where the cyclotron mode was basically much higher than the axial mode, was then much higher than the magnetron mode. These are the frequencies of these modes as a function of like how much magnetic field is applied. And in a sense, this regime comes when you close this gap between the two modes, and it's all the way down here in a totally different regime of operation, but we think one that's accessible for us. So the nice thing about having arrays which are defined by patterning electrodes is that you think you should be able to design what those look like. So for instance, you can think about whether you go for hexagonal lattice patterns, but there's even interesting aspects with relation to the magnetic field as compared to the plane of the lattice. So imagine that the plane of ions is in this direction and I change this angle theta. Then we can look at what the normal modes are, and even within just one of the bands, then we can see that for some angles of the magnetic field, there's a band gap essentially, and this band gap closes up for other angles of the magnetic field. So somehow we can choose normal mode structures, I think, to do interesting physics here. I don't know quite what the best physics to investigate is. We've chosen to be a one particular parameter set for our first experiment, but I think there's lots of flexibility and possibility for interesting models. So I just wanted to mention this enhanced 0-point motion. I won't go into the physics of it, but it's got all sorts of nice features. It increases the couplings between separated ions. It increases the coupling to laser fields. The bad side is that it probably increases the heating rate of the ions, though kind of a nice feature is it still samples the noise at the bare frequency of the oscillator, we think, at the moment. So we're kind of intrigued by that feature. I see I'm running out of time, so let me just quickly say that we've sketched out then a model for doing quantum computing in a lattice, which had very promising parameters for us. We were happy to see, if you like. But the other thing that it frees us up with in the context of quantum computing is one of the things we look towards is this quantum CCD architecture where ions are moved around in 2D, but one of the really big challenges, as I said before, was going through these two-dimensional junction regions, because this RF pseudopotential is fundamentally a 1D null. Yeah. So just an example of that, here's a design in my lab by one of my students, and what we would see coming into the junction is actually that the driven motion of the RF is 3 microns, which compared to the ground state wave function is 100 times the size. So anything we don't do well here has a potential to severely impact the performance of this system in terms of its control. And the nice thing in the penning trap is no RF, right? So basically, because the magnetic field is homogeneous, then what one needs to be able to do is just to move ions using their static potentials, and there's no real constraint on that. You can move in 3 dimensions as long as you move these static potentials in 3 dimensions. So the flexibility of tuning around these traps should be greatly increased and should facilitate much parallelization, if you like, of the control. So all of a sudden, we think it's interesting to pursue even, and maybe that's more interesting from as a sort of jump, it may be more interesting than the quantum simulation to go directly for quantum computing. So are we realizing it? Well, we have the magnet. It looks a bit like Thomas the Tank Engine at the moment. It's got a chimney, right, and a big case. We're starting to put together the vacuum system. It's being tested in the last weeks. We've made chips and things like that. So here are the open questions. Can we get good coherence? Can we load at all? And what are the heating rates like in these small penning traps where there's no RF? That's actually a fairly fundamental problem that everybody who measured a heating rate in an ion trap till date had high voltage RF applied, which presumably drives processes in the electrodes. And it would be very, very nice to just measure that in a static situation, which the penning trap provides. So with that, then I thank you for your attention. I hope you've got more questions, and I just point out some of the people who inspired our ideas. They're highlighted in red, if you like, and who've been working on this particular project.
Thanks for the very nice lecture. I think there are a couple of questions, at least the one I see, new one from Abhijit. A general question, can you elaborate on your statement that 1 million ions are required to build a quantum computer?
Yeah, sure. So, I mean, essentially, if you want to do a quantum computing with error correction, and you want your error rates to be low enough, then you can do estimates of what you need to do. For instance, the example that probably comes up with this 1 million ions, I have 2 examples in mind. One is to do Shor's algorithm so the error rate that I think I've seen quoted that you might need is about gate errors on a logical qubit of around 1 part in 10 to the 15 to make a Shor's algorithm work. And you might need the 1,000 qubits that are that have that error rate. Yeah. And then what that means, if you look at some code like the surface code, is that basically means you need a factor of 1,000 in qubits to be able to correct errors to that degree, even if you have fundamental in your lab gate errors of 1 part in 10 to the 3 or better that we like. Well, I should say that even if the error rates that you achieve are a factor of 10 or so better than we can achieve in the lab today, then you still would require this factor of 1,000 overhead. Yeah. The same is roughly true for doing quantum chemistry in a fault tolerant setting. So of course you would say, well, but lots of people think they can build a quantum computer today, right? I would say that yes, but those systems are highly faulty, right? So it's a gamble. It's a question of, can you find things that allow you on a very faulty machine that basically works half the time or something? Can you find any advantage out of that machine from the fact that quantum mechanics gives you more power than classical physics for computing? I think nobody knows the answer to that question. A lot of people are putting a lot of money, gambling that the question is yes, yeah. And you will find a variety of opinions. Probably people who work in business and need to raise cash need to be more positive about that statement than I would, but that's basically an unknown, I think, genuine. Yeah. So we might strike lucky, but I think anyone who would say this is when we know a quantum computer could offer you an advantage would have to tell you, but it will require 1 million, and it'll require them operating a factor of 10 better than we can today, and requires, yeah, this sort of scale of device. Yeah. So my statement would usually be that, you know, for these, anyway, my interest is often more cited on error correction than algorithms, but for these sort of error corrected systems, then this is why there's still many years to go before we build quantum computers that are serious. Yeah. Yeah. But much interesting physics to be done on the way there, I should say, right? So I'm very enthusiastic about today's devices, but they're not necessarily computers. Yeah, that's what I would say. Yeah.
Okay, I think that's one. I have a question regarding the, when you mentioned that you are interested to measure the heating rate. This is a big debate always with traps, and particularly surface traps. Now, what do you think it would be? And it's a prediction, right?
Yeah, I think I wouldn't like to say, because it's the heating rate is not a well understood, like what's the cause of this noise is not a well understood process, right? So I think my only statement would be that, you know, a lot of it seems to be some sort of activated process of migration on the chip surfaces. And to me, having high voltages oscillating backwards and forwards with light particles, like, you know, the sort of charges you get in materials, seems to be something that potentially will affect what goes on in those surfaces. Yeah. So in that sense, then I think it will be very interesting just to get rid of that for once in a while. And to me, it's quite an important data point actually to maybe give us more information actually about what we could do about it.
If I understand you correctly, that you would expect to see less here. At least the scaling would be lower compared
to.
Yeah,
I would more say that I would hope to see less. I guess expect would say that I had a theory of what's going on, and I wouldn't say we have a good theory of what's going on. So
right. It's a very open question there.
Yeah.
Okay. So any other question from? This is your last chance. Ask now. Yeah, now it comes. Yeah.
So it's a nice talk.
There is a question here. Sorry, there is a question here. Can we go through it now?
Yes, okay. You can take that question.
Okay, so this is from Noah again. I think the question is, what are the limitations of this spinning ion lattices from the point of view of quantum computing?
Yeah, okay, so I didn't mention that. So I guess, did I mention the frequency at which they're spinning somewhere? No, probably not. So let me just say it here. So the sort of frequency at which you have to spin this thing up, and now you have to imagine that this is rotating, is sort of 160 kilohertz or something like that, yeah, or tens of kilohertz, let's say. So what this means is that this picture here, which looks very beautiful, and it is very beautiful, is actually taken with a stroboscopic camera, right? Every once in a cycle, you go looking for the fluorescence, right? And so one of the challenges in trying to build that into a quantum computing system is then not only to do imaging like that, but also have individual laser beams, arrays of laser beams that you have to get into a bore of a magnet, for instance, which can then address individual sites in this lattice and perform control there. Yeah. The other challenge in this sort of any sort of structure like this is that though I talked primarily about these drumhead axial type motion, there are in-plane modes of this lattice too, and these are at low frequencies, right? Ultimately, it comes down to a situation where I would call this a bulk system. And bulk systems, if they are highly anisotropic, tend to have low frequency modes, which are existing, yeah, structural type modes. And that's what's happening here. These in-plane modes are actually magnetron type modes, right? And they're at low frequencies, and there is a lot of them. And what they lead to is just, it's a many-body system, it's a more complex system, it's they lead to instabilities and things that we wouldn't necessarily see in results, right? But they're hard things to work with, yeah. And I think that's sort of true. If you think about scaling these systems up, essentially you will run into the limits of those sort of problems, yeah, at some point. The other thing to say is that indeed to have a larger and larger crystal at some point, if you think about me talking about 1 million, then you start to get to size scales which are quite considerable and need voltages that are high or whatever. And so some of those considerations are sort of longer term challenges, I think. But, you know, one of the states of the art things that they're doing in this system today is trying to get this more local control, right? And part of that is stroboscopic. And one thing they've actually done there recently, which I didn't have time to put in, was to put in essentially standing wave structures which rotate along with the crystal at some level, yeah? And these then allow you to imprint a static, in the rest frame of the ions, a static structure, which gives you some individual control, yeah? But this is still something in development, so it's still something that they, it's not easy for them to do that. Yeah. Yeah.
Okay, I think there is a last, I think it's more a very open question. It's, if we have to buy a quantum computer, what should one look in terms of rating, which I guess
Yeah,
it's in terms of quality, I guess.
Yeah, I think that, I mean, you probably want to know, as with any computer, right? You probably want to know what you want to do with it at some level, right? So there's probably some particular algorithm, and then I think we're in a very nascent period with respect to doing these algorithms, right? Because there are many factors that will affect both how large your computer is, i.e. how much error correction do you need is a major question, which relates not just to the rate of errors, that's kind of a simplistic notion, but also what type your errors are. Do they have correlations that are spatial? Do they have correlations in time? And if you like, this is the frontier of research in quantum error correction experimentally, at least, is discovering how different types of errors, not theorists' errors necessarily, propagate in these complex systems, actually, yeah. And in the presence of measurement and feedback and all of these sort of aspects, yeah. So I think it's very hard to make predictions about what systems will come out in front in the end. That's why, in a sense, lots of systems still exist, yeah. You can point to certain features that would say you can win. So, you know, as an ion trapper, I would probably say, well, look, our error rates for 2-qubit gates are the lowest, right? And that will enable us to build a smaller computer with less error correction. And hopefully that's a good thing, yeah. On the other hand, in superconducting qubits, they might say, well, yeah, but every gate you do is 100 times slower than the gates we do, yeah. And that's a totally valid point, yeah. But I would then say, but your noise is worse, and how do you deal with that? So I think this, in a sense, you know, the reason I got into this field in the first place was because what I like is you can go to a conference and there are people working in solid state physics and people working in atomic physics and people working in other stuff, and they all kind of speak the same language, right? Because they have this common set of things that they're trying to do with very diverse systems. And it's still fun to me to see how the thinking of those diverse systems plays off each other. We've had a very nice relationship, for instance, with the Shulkov group at Yale, or Devereux group at Yale, in terms of some of the motional codes that I tried to show you last week, where their ideas sprung our ideas and the same thing happened in reverse. And it's because we were doing the same things in different systems. Yeah. And this is where innovation kind of feels like it came from in that sense. I very much enjoyed that.
So I think with this very nice notes, we can close this session. It's very nice lectures, John. Thanks for the lectures. I believe the students gained a lot from this. Thank you. Take care.
Listening, and yeah, thanks for the questions.
Thank you very much.
Yeah, thank you very much.
Yes, yes.
So hand over to you.
Yes, Professor John, it's quite interesting talk, and I think that the participants have learned about the physics. So, Sourav, we can close now, or?
Yes, we can close. Today we're meeting at 8:30 again, right?
8:30.
Yes. Okay.
Okay, yeah, bye.
Saikat. Okay.
Yeah, so is ICTS, they will send a mail, no reminder, or should we?
They will probably do it anyway. I think they have already done it. No, is it? No, I don't know, but I think they'll do it.
No, there is no mail.
Yeah. So I can ask them to send an email, not a problem. Typically, they do it in the evening. So
Usually, yeah, usually they send.
yeah. Okay. Okay.
Okay, yeah. So let's meet at 8.
8:30. 8:30.
8:30.